of National Workshop on Radiochemistry and Applications of Radioisotopes. So there is a small change in schedule. Now we will be having a lecture on application of radioanalytical techniques in research by Dr. P.S. Ramanjaneyulu garu. So now I welcome Ramanjaneyulu garu to continue his talk on application of radioanalytical techniques in research. Sir, welcome.
Thank you, sir. Very good morning. ఓకే ఏంటి గత 3 రోజుల నుంచి విని అలసిపోయారా ఏంటి? ఎవరు గుడ్ మార్నింగ్ చాలా స్లోగా చెప్తున్నట్టున్నారు. ఓకే, టైటిల్ ఆల్రెడీ ఇక్కడ నేను డిస్ప్లే చేశాను ఆల్రెడీ. అప్లికేషన్ ఆఫ్ రేడియో అనలిటికల్ టెక్నిక్స్ ఇన్ రీసెర్చ్. ఓకే, ద మెయిన్ ఎయిమ్ ఈస్ దట్ ఇఫ్ యూ వాంట్ టు డూ సంథింగ్ రీసెర్చ్ ఇన్ యువర్ ఫ్యూచర్, if anything problem we are facing in your research career, if you have to quantify something element, there may be huge number of analytical methodologies are available. You can choose one of the method as a radio analytical techniques. That is what my aim. My aim is not to make you expert in this field. I just want to give what is the flavor, what the different types of approach we can go for this radio analytical techniques in your research career. The what are the examples I have showing is already done. It doesn't mean that the same thing you have to repeat there. Okay, these are the way of approach I just want to explain to you. In your future research you can explore this type of techniques in your research career in the future. Okay, for solving any analytical problem, some crucial steps are, if you want to choose anything analytical problems, there are so many ways will be there approach. The same way they will amar telulo untundi kada, నీ ముక్కు చూపించాలంటే అలాగే చూపించవచ్చు, ఇలా తిరిగి కూడా చూపించవచ్చు. ఓకే, దేర్ ఆర్ మేబీ డిఫరెంట్ వేస్ విల్ బి దేర్. నౌ choosing the right method, see there will be no good or bad methods. Every method have its own advantages and its own limitations. Depending on your problem we have to choose the right method. Okay, means with the minimum efforts we have to solve our problem. The way we have to choose the right method. Then understand the signal generation is in this method, how we are getting the signal. If you understand properly the how you are getting the signal, then you can see that where you are lacking or where you are doing mistake. If anything problem, what the way you are expecting it is not coming, you can back see that one, why we are not getting the proper signal, you can understand that. Then improving the signal by noise ratio and its measurement. If you see the how the signal is generating, no, then you can improve some other ways to get the better S by N ratio and its measurement. And any analytical problems, because you will not see that entire matrix, you take the sample and do the analysis. Definitely you are taking very small fraction from what your matrix is there, and then you are preparing the sample. Then this sample should be true representative of your the matrix, right? No, suppose if you want to see something, what is the water contamination in Godavari river, some other elements you want to see, you will not definitely will not collect entire Godavari river to here, no. You will take some small sample from the water, right? No, then that should be true representative. Then you should not be like that, you just go for the bank and you will take the one sample here. That may not be true representative of your entire Godavari, what the reservoir is here in the Dhavaleshwaram barrage. The maximum as possible you will go to the center by boat and take the different locations water, then you will mix it, uniform it, then homogenization, and then take very small amount of sample from that, right? No, the same way this type of procedure you have to follow when you are collecting something samples from the matrix. And then sample preparation, see once you are collected the sample, the same type of sample maybe you are not injected into what the analytical methodology you are using. There may be some sample preparations may be required, maybe you have to do something solvent extraction or ion exchange, or maybe you have to keep it dry, something like that, no. Then that sample preparation should be, you have to make sure that what the element of interest where your interest is there, that should not be loss or contamination, something should not be there during your sample preparation. And then measurement, See, it's not like that just the way we are on the telephone or anything, just keep it on, immediately it will start. There may be some analytical methods, instruments, maybe it requires some stabilization. Then you see the measurement like stability, reproducibility, that everything you check it and then you go for your sample analysis. The conversion of signal to concentration, any methods you will see that directly it will not show the concentration. Suppose in the case of like absorbance, you must be all knowing about the spectrophotometer, where you will get the only absorbance. From the absorbance you are converting to the concentration by using the well known scientific laws. Okay, the same way, like suppose you are measuring some activity, you will get the counts. From that you are maybe converting to the concentration or amount of analyte, something like that. No, that the conversion should be, you have to understand properly the what is the relation between your signal what you are getting and then whatever your measurement concentration. And then evaluation of errors or uncertainties, means in these methodologies what are the errors, see what are the value you are getting, how much you are accurate. To see that you have to see the error, all the errors you have to cumulative, the error propagation laws you can apply, and you see that how much of what the analytical data you are getting, how much you are sure, how much confidence you have on the results. That can be get it by using the evaluation of errors. And then documentation protocols, see whenever you are reporting something value, there should be some protocol, what is the confidence level and other things. Then observations and raw data calculations and everything you have to do it. Then interpretation of your data, finally you are interpreting. See, based on this value I can say that something Godavari water is getting contamination of this may be because something industrial waste or sewage waste, there is some contamination. From your data, when you are interpreting your data, then this all proper methodology, proper way we have to approach. Finally whatever you are giving the interpretation of the data will have something meaning. Otherwise it will give something like that you are deviating from the actual issue. Okay. Now see, in this all methods what I will say that there are different approaches are there. Now one example where I am saying about the radioanalytical techniques. The radioanalytical techniques that deals with the radioisotope tracers or induced activity and measurement of radiation. These all radioanalytical techniques, whatever we are saying, maybe you can take something like isotopes as a radio tracers, or you can induce the activity either by meaning of like bombarding with some neutrons or accelerators, some charged particles, accelerated particles, and then either radio tracers or you are inducing the radioactivity, and then you are measuring the radiation. Finally we are measuring the radiation. From this we are doing element of interest, how much we are do the calculations, and then we are doing something interpretation based on your results. A few methods and applications will be described in the next few slides. Before going to the actual methodologies, we will first like we have to go for something like history. The pioneers in this radio tracer or radioanalytical techniques is George Hevesy. Before going to this, I just wanted to say something story about for the students. Hevesy is a chemist, and he's done the doctorate degree in the Germany, and at the around 1911 or 1912, just started the First World War. Then he shifted to the England and he joined with the Rutherford's laboratory. All of you know the Rutherford is a physicist, and at that time just radioactivity is discovered, and he has done the RBS, Rutherford backscattering technique, and other experiments he has done. And that simultaneously the Madame Curie also discovered something radioactivity from the radium. Now Rutherford wanted the decay products of radium he want to use for some other application. Then he called the Hevesy and asked that you separate the daughter product of radium and from the pitch blende, and there will be so much of lead is there, you remove that stuff, the lead, you separate the lead, and I wanted the daughter product of from the radium. That the task he has given to the Hevesy because he is the chemist. Now by using something various approaches, he tried to separate the lead from this radium daughter product, and he is struggling a lot, and they have very similar properties of chemical nature, and he is struggling. And in this simultaneously when he shifted to England, and he is staying as a one paying guest. Okay, when things are not getting what the way you want, no, everything you will be bothered for you, right? No, you will not get the proper sleep. For anything small disturbance also you will feel something irritation. These all are common nature for all human beings, right? No, the Hevesy also not like a normal human being, is also bothering one more thing for him. What he is suspecting as a paying guest, no, the bread whatever is given to the yesterday night, the whatever is left over, the same thing she is keeping on the refrigerator or whatever, and next day she is serving. He got that as a doubt. Then the where he is struggling, like lead radio trace or something using to separate, he is not able to succeed that. Then he thought that same activity he brought, applied on the bread, okay, and then he left without eating anything. Then as usual, the lady that taken that, the next day he again same bread she is provided to him. Then instead of eating it, he went to the lab and measured the activity. Because that lady doesn't know that, because it doesn't have any smell or anything, no. The activity doesn't show, we can't see it by naked eye. Then he identified that the bread is contaminated with the same activity whatever he applied yesterday night. That is the first application of radio tracers. But finally, the later he came to know that the what he wanted to separate is nothing but it is only lead only. It is a different isotope of lead. Which one you want separate from the lead? That's what he could not succeed on that. But these all struggles, he made him as an expert in the chemical procedures. Maybe all of you may be knowing that the hafnium, the atomic number 72 is discovered by FSA only. This is whatever, he is a wonderful chemist at that time. Then he applied his whatever he struggled for the separation of lead, and from this, that same thing he applied in for the separation of hafnium from the zirconium materials. Then he discovered the element of 72, that is the hafnium. But he got the Nobel Prize for the application of radio tracers and radio analytical techniques, especially neutron activation analysis. He got the Nobel Prize in 1943. Just only for story Thursday, I just wanted to say. Then the radio analytical techniques, there are the direct methods where the way we are getting something activity from the uranium ores or uranium samples, the directly we are seeing the activities releasing from the same sample that we measure, that is called direct methods. Suppose if you want to say something like non-destructive methods like nuclear materials, plutonium based or something like that, what the activities releasing from the sample directly we are using that one, which are called direct methods. If you have the indirect methods where the activity is not available in your sample, now we have to induce it. Okay, the induce means there is maybe something like addition of radio tracers, because when you add something radio tracer, they chemically behave identical way. You can add something radio tracers and you do your methodology procedures. We can see that one. Or otherwise neutron induced, you go to the sample and irradiate in the nuclear reactors or isotope sources, where you will get the like a neutron activation analysis or prone gamma neutron activation analysis. There's two different ways are there. And also you can induce the activity by using the charged particle activation. Means you have to go to for the accelerators, you accelerate the charged particle and then bombard. But in the case of neutrons, I didn't say that acceleration, but here in the case of charged particle, I am saying it has to be accelerated. That maybe the difference maybe you might be knowing, because when I am going for the charged particle, there always will be one Coulomb barrier will be there. Unless you cross the Coulomb barrier, it cannot go and interact with any other nuclei. To cross the nuclear barrier, we have to always accelerate the charged particle and then bombard your sample or whatever the target. And there are so many ways of approaching in the charged particle activation, like a nuclear reaction analysis, particle induced gamma ray emissions, Rutherford scattering, and particle induced X-ray emission. There are so many ways of approaches are there. In these all methods, we are measuring the radiation. Is nothing but you already knows alpha, beta, gamma, and fluorescence. Even XRF techniques also they will be considered as one of the radio analytical techniques, because where we are using X-rays for the generating the fluorescence, that will also treated as a radio analytical techniques. Okay. Some important features of detectors, because when I am using the radiation to measure the detectors we have to consider. Yesterday you are already learned about the radiation detection and measurement. Then how to select which detector we have to choose. Yesterday someone asked me about that, how you select this. You are saying for gamma measurement sodium iodide. If you want to go for the beta measurement, you are saying GM counter. Then how to choose the detectors. When I am seeing the radiation measurement, we have to select which is the best detector, and when I am selecting any detectors, what are the parameters you have to consider. The one is the efficiency, which is the more efficient detector for what the radiation we are interested to measure. Then what is the energy resolution. Why I am saying energy resolution, there are maybe so many different ways of radiations may be coming from your sample, that what you are measuring exactly, it is mean for your where you are interested or not. That will dictated by the energy resolution. Suppose the resolutions are very good, then what the activity you are measuring, it may be exactly what you are measuring. The other interference may not be there. If the resolution is poor, that maybe some other radiation also interfering where you are measuring. Then depending on your application, we have to choose that which is the energy resolution, and then linearity, because see the when you are any methods, you will do something standards and other things, they have something measurement range at one concentration, in actual sample at maybe different range. Whether the same linearity, same laws will apply there or not, we have to see, that is dictated by the linearity. The way like spectrophotometer, when you apply, you will do something calibration range at different concentrations of like iron 110 phenolphthalein complex. You all must have done in your BSc standards that different concentration take, you will take iron and you complex with iron 110 phenolphthalein, then you will see the absorbance measurement, no, and then you will make a one calibration plot. And yesterday also you heard some of the people have done the calibration in the energy versus your potential. What do you call? There's a potential only, no? Chandrasekhar? It's the potential only, no? What is the pulse height basically? What is the potential pulse height you are getting in the radiation? That also you have done the calibration. The same way we have to see that what are the measuring parameter and concentration or whatever, you have to make something relation between the two parameters, that is called, we have to see the linearity. And that time, suppose the activity what you are measuring, it is so high that maybe the some of the incidents maybe you are missing, but from this we are interpreting something concentration, you are doing the calculation. We have to see that what is the dead time of your detectors, and also the ease of manufacture. It is not like that something I wanted something very high profile instrument that may not be available as per your financial constraints and other things, or it is easily available in the market also for us. The ease of manufacture, maintenance, cost, these all parameters you have to consider when I am choosing which is the detectors you have to select for our application. And there are other detectors like ion chambers, proportional counters, this all you have learned yesterday. Then if you use the ion chambers, you see that efficiency wise is the poor, but resolution is okay, but the cost wise low. This is very good for us. If you want to measure something like alpha or any charged particles, we can go for the ion chambers. Then there is the one proportional counters where the efficiency will be okay and the resolution is good and cost wise also is low. In the case of GM counters, this is one is the gross counting we can go, and the spectro only gross counting. The one I replied is only for the gross counting. The GM counters only for the gross counting we can see, because there is no resolution. It cannot identify what is the energy of your radiation is emitting. The efficiency wise is okay and the resolution is nil, because it cannot identify any what energy of your particle emission, and the cost wise so very low. In the case of sodium iodide, cesium iodide, that already are experienced in our single channel analyzer. The gross counting, of course we can go for the energy resolution also, and the efficiency is good because we are using the well type of detectors, and resolution is poor, and then cost wise medium, like zinc sulfide, organic matrix, like HPGE for all the types of gamma measurements, and it's a spectrometry. Actually the resolution will be very good, efficiency is okay, it may be compared to sodium iodide around 30 to 40% you will get. Resolution is excellent, it's around resolution of only 1 or 2 keV, and the cost wise very high, depending on your application and what your financial constraints, what is the budget availability, and whether you have the access to that instrument or not. This all based on these all conditions, you have to choose one of these detectors to measure your radiation. The analysis by means of natural radioactivity, as already we have done in the separation science experiment, we can use what are the activities already coming from your element of interest that can be used to for the measurement. The essentially natural processes like radon or natural decay series and other things we can go. The anthropogenic, suppose someone is doing something uranium mining, then someone is suspecting that something activity is spreading to the surrounding areas or not. You can take something soil sample from the surrounding areas, you can see the radioactivity, anything spread is there or not. Or the same way, there's something there, someone is doing the processing, some elements are processing or radioactive sample they are processing, whether is there any contamination in the surrounding areas they can check. And also does something diagnostic purposes, like see any for healthcare sectors, if you have anything problems in the how the kidney is functioning, you want to know, they will induce something radioactivity in your body, and then they will see that how your body is functioning by just taking some images. The images they are getting from the measuring the only gamma ray emissions. From that they have the images they will get, from that they will see that how your kidney is functioning, your liver is functioning, like that. Anyhow you will came to know very soon in the next lectures. Dr. Tapas Das will explain about this all. and then some testing purpose or any accidents, something nuclear accidents maybe happened like Fukushima or Chernobyl, something like that. The how it is spread, activity spread, that you can see that something radioisotopes which is coming from the sources and how it is spread, everything we can see. These all measurements, I have not added any external activity. Whatever activity is coming from the sample or element of interest, that we are using to measurement, that is called as the natural radioactivity measurements. Okay. Now the example like the potassium can be analyzed by measuring the activity of potassium 40 is having the abundance of, in the natural abundance 0.0117 percentage, the abundance is this much abundance, and T half is 1.277 10 power 9 years. I think Atanuja has already demonstrated you all. You just taken the potassium iodide, you can take any sample from your chemistry lab also. You can measure the activity by using some gamma spectrometer, and then suppose in case you want to estimate how much of potassium is there from this half-lives and abundance, maybe you can calculate how much of potassium is also there. This is only just one example I am saying. And if you see something natural radioactivity, you can take any banana from whatever we are getting. I think it's East Godavari is very famous for our banana. You take any banana and you see that how much of activity is coming. Then from that we can see that how much of potassium is there in your banana. Like our coconut water, these all things we can do it. Okay, just for saying that beta decay, and it will emit 1.33 MeV of gamma ray, and then along with that, the beta decay of having energy of 1.33 MeV, along with that one gamma ray is emitting, that is 1461 keV. Okay. The example like polonium, it is also natural decay series, and along with that alpha particle is emitting with a T of 138 days. This like maybe you do something separation by polonium, and then you can deposit something silver foil, and it can be measured by like a proportional counter or any gamma alpha spectrometry. From that we can see that how much of polonium is there in your sample. So there are some examples only I mentioned here. Then radioisotope application in chemical research, because we are the chemists, that's what I given as a chemical research. It doesn't mean that it's only for chemistry related. You can apply any scientific problems. In the research of something like if you want to see something reaction mechanism, there also you can see something application of radioanalytical techniques, and if you want to see something kinetics parameter, there also you can apply some of the examples I will describe here. And if you want to see something exchange processes, that also you can apply something radioanalytical techniques to see how the exchange is happening or kinetics in this. In the field of analysis of like radiometric titrations, isotopic dilution analysis, solubility product determinations, these are the well established examples for the application of radioanalytical techniques. And also you see the efficiency of general chemical processes like a precipitation, filtration, like extraction of or ion exchange studies or separation. These are all the some glimpses only I want to give. You know, within 1 hour I can't describe entire about the radioanalytical techniques. Some of the examples I will discuss here, where there is unique methodologies of application of radioanalytical techniques in our research. You see the radio tracers have been widely used in chemical research. Why we are saying the radio tracers? Because the advantage is simplicity and sensitivity of the technique. Suppose if you want to see something iodine, how it is migrating in your process, you take something tracers, and then because both are chemically same, the radioisotopes are used in a very small amount, and then the radio tracers are very easy to detect and used to investigate the different types of physico-chemical process and in analytical chemistry. Because the radio tracer and your element of interest both are chemically same, and they will behave the same manner, and from this the tracking the radioactivity we can see that how they are processing, how they are migrating, then how they are getting precipitated. This all we can see, and because of very good efficiency detectors are available now, with a very small amount like some few micrograms, we can take the active amount wise, or in the activity wise something like microcuries you can take and do the what the analysis you are doing. The application of radio tracers are based on the fact that isotopes of element behave chemically in a similar way. Because both are chemically same, they behave the same way, thus remains invariant through the course of your physical, chemical or biological process. The whatever process is happening, either a chemical, something like getting precipitated or maybe forming something complex, both radio tracers and your element of interest will behave identical way. And also something biological process also, because both are chemically same, our biological process also depends on the chemical nature, Then we can see that how it is migrating, I mean how it is penetrating to your body, something like that we can see. The okay, if a radioactive isotope is added externally to a mixture of its naturally occurring isotopes, it serves as a tag or a label, and this permits the path of the element to be traced during any change. The element that is tagged is called a tracer element. As I mentioned, Heavisey also used enormous studies about your application of radio tracers. He is only the first person applied some radio tracers in your water body system. Then if you take something water, how much time it will take to get out from your body, that all parameters he established at that time, is the early of 90s. And also I think something rat, he took something water, how if you inject anything water, how much days it will take to get out from your rat's body. These all studies have been done by Heavisey, and it's almost like 100 years back they have done these all studies. The practical considerations in the radio tracer experiments, the first is that what the practical consideration, the availability of radio tracer, whether what the element of your interest, whether radio tracer is available or not, and with proper off-life or particle energy and specific activity. Suppose maybe radio tracers are available, that may be available in the in Mumbai. By the time you reach it here, it may be not, should not be decay. Then you see what is the off-life, and what is the particle energy, what is the emission, whatever you are getting from these radio tracers, whether we have the detection to suit the requirement or not, and what is the specific activity. Then based on that, how much of tracers could be added, everything you have to see. The short half-life avoidable because the decay correction is needed. The way, I mean, when you are getting from the transporting from some other sources, the short half-lives maybe can be avoided, and very long half-life is also avoidable because the disposable problems. Your application should be like that, you use it after your application, end of your application, you keep it for some time, then it should become decay completely such that you can process like a normal waste. If it is very long half-life, then you have to special care has to be taken for the disposal. And like oxygen, nitrogen does not have any suitable radio tracers. The radio tracers are not available for all type of elements. Example like oxygen or nitrogen, there are no tracers are not available. That emitted radiation should be easy to detect. Suppose you have something like sodium iodide single channel detector, then you want to measure something like only beta is emitting. That may not be possible by using your detectors. So what are the emitting radiations? These all considerations you have to consider when you are selecting something radio tracers. And the specific activity should be high for better result. As I mentioned, if specific activity is very high, you could take very small amount of tracers like microgram that is not affecting your the main process, then we can choose the application. Like if an example I am saying the reaction mechanism, the sodium bisulfite Na2SO3, if you treat with HCl, we are getting the NaCl plus H2O and sulfur and SO2. Now here are two sulfurs are there. The one sulfur I am getting as a precipitate, okay, free sulfur I am getting. Whether is getting is one of them or only one, both are same or not, both the sulfurs whatever it is there, one is forming SO2, another one is only free sulfur. Whether this bisulfite both are same or not to identify, there is no other method can do what we are saying. That is only possible by using something like that radio tracer methods. When you are making the sodium bisulfite, you label something sulfur 35 radioisotope and then do the same reaction, then you see that what type of sulfur you are getting, where activity is getting, whether the sulfur dioxide or sulfur free sulfur. From this we can identify that both the sulfurs are not same. That means if it is equivalent position, it should be like this, and non-equivalent position should be like this. Because we got only one type of sulfur only in this case, that means both the sulfurs are not equivalent. Bisulfate structure should be like this. Okay. If you want to identify this type of mechanisms, the radio tracers are one of the best techniques to identify this type of problems. Again, if you see the barium sulfide and you have something sulfide, the solution, if you add something barium, the barium sulfide is getting precipitated but is sparingly soluble. But now this sulfide is continuously exchanging with the barium sulfide. This is always like equilibrium. Now the system is in equilibrium at all time. So how to measure the kinetics of exchange? How the sulfide is exchanging between the barium sulfide and in our solution. Suppose if you want to see the kinetics of this reaction, because in a chemical procedure we will see only sulfide concentration will be remain same because already at equilibrium. Okay, if you want to see sulfide concentration, you can't get it. What the kinetics of exchange? The radio tracers can be applied here. Now the can be measured by monitoring the decrease in the activity of sulfur. Sorry. The kinetics of can be measured by monitoring the decrease of activity of sulfur 35 in the solution from time to time. Then what you want to say that you dope the sulfur 35 here in the sulfate, and you see that how much of activity is decreasing with the time. From this we can determine the what is the kinetics of sulfate exchange with the barium sulfate. The same way, like if you take a sodium boride and methyl boride, it will form like NaBr and C2H5Br. This continuous exchange is happening here. Then because both are chemically same, if you want to go for any chemical method, we can't see that how they are exchanging happening. But if you use the radio tracers, we can see that how it is getting transferred, the what is the kinetics of these transfer rates and other things. The same way, if you have the iron 2 and iron 3, the continuous reduction and oxidation is taking place. If you want to see that what is the rate of these reactions, we can use something radio tracers of iron 59. From that you label with something like ferrous, then how much of activity you are getting in the, with the ferric we can see. From this we can see that what is the redox or oxidation kinetics. There are some examples only I am telling. In the real application wherever you are facing something problem, you can choose this is one of the way we can solve your problems. Okay. The no new chemical species are produced in the system, remains unchanged. The isotope exchange reactions are very useful for the synthesis of labeled compounds. Suppose if someone wanted to label the methyl boride, you can take the like sodium boride with labeled one. After something exchange, because of exchange reactions, you will get in the organic boride form. Like suppose you have the precipitation like KCl, if you take, I think you all must be done in your BSc graduation level. You add something AgNO3, the silver chloride will get precipitate. Now if you want to see that how what is the end point of this precipitation titrations, we can take something tracers of silver 11010 in the labeled with AgNO3. If you are doing the titration up to the precipitation is over, the activity will be remain same, because the one it will get the precipitation, you all of you know, the when the solubility product is reached, the ionic product is cross the solubility product, then only you will get the precipitate. Up to the solubility product is remain same up to your end of your precipitate, then remain solution activity will be remain same. Once it is the precipitate is over, whatever silver you are adding AgNO3, it will be remain in the solution, hence activity will be go up like this way. You can see the identify what is the end point in this type of titrations. The very simple examples only are taken because you all are belongs to the physics discipline. The simple examples I want to explain what is the application of radioanalytical techniques. Suppose if you want to see the determination of total volume of blood, suppose if you want someone want to identify what is the how much of blood is there in your body, so definitely I cannot suck entire blood and measure it, no? Definitely by the time patient will die. Then some other ways you can think. Then the one is the radio tracer method is the one of the best example application to see what is the total volume of your blood. That is called isotope dilution method. Now the applicable to this cases where the quantitative separation becomes impossible or time consuming. This is not only for one blood sample only I am taking what is the total volume of your blood. Suppose in some of the cases its quantitative separation is not possible, you can use the isotope dilution method, and then we can see that. The simple example way I have written, this is the tracer I have taken. You see how many total circles are there with the cross. These all are active one. Out of 12, every one is active. Then total is 12 and specific activity will be 1, because out of 12 every one is active. Now this is your sample where you are doing. This nothing activity is there. You can see how many are there. This you have to measure now. That like total volume of your blood. Now you inject something radio tracer into your blood system after certain time of equilibrium. When a small fraction you take it from your blood sample again, and you see the what is the specific activity in this. By using the isotope dilution principles, we can see the calculate the values. The same thing, nothing but specific activity into your final volume and then specific activity into volume of your initial cases. By solving this equation, I can determine what is the volume or Wx in this case, or in our case like a blood, what is the total volume of your blood we can be determined. The example is that there is no need of any quantitative separation. The 1 ml of blood from the patient is withdrawn and is labeled with 24 sodium chloride, 24 sodium, and with half life of around 15 hours. The specific activity is being around 20,000 CPM per ml, and this is injected in inventory through the patient. After about 15 minutes, 1 ml of blood is withdrawn and from the patient, and the activity can be measured. From the how much of specific activity in the blood sample in the sample, from this we can determine what is the volume of your blood, and they are identified something like that. In that case is around 5 liters. Okay. The radio tracers are effectively used to determine the solubility of sparingly soluble salt by tracking either metal ion or one of the atoms in the anionic radical, like something in the case of lead iodide. You can either label with lead or iodine. We can see that how much the precipitate is getting, and we can see from this. And if anything, someone is want to do the filtration efficiency, some filters suppose you are using, then what is the efficiency of filters also can be done by some radio tracer technique. And to check the complete washings of your precipitates, suppose some precipitates are formed and you are washing, whether during this process elution is there or not, this all can be done. The losses due to your washing, this all can be applied your radio tracer techniques to see these all parameters. In case the studies on solvent extraction or ion exchange or chromatography, adsorption chromatography, then we can apply something like radio tracers. Suppose because these all process have something like exchange equilibrium, from this the activity in the organic phase or activity in the aqueous phase, from this we can determine. So some of the people have already done the solvent extraction experiment. From this radioactivity measurement we are determining the what is the how much of percentage is getting extracted. The same way we can also determine what is the diffusion distribution coefficient by measuring the activity in the different phases. And also one of the example is, suppose someone wanted to see that what are the fertilizers we are using for our plants growth, whether how much it is taking up. Suppose someone wanted to try that, one of the best example is the phosphorus 32 you can take, then you radio tracers you take up phosphorus 32 and add in the fertilizers and do your application in your fields. After certain time you can see that how much of phosphorus inject taken by your plants. From that we can see that how much efficiently your fertilizers is working. So one of the example, maybe you can see some other options also. The solvent extraction, already some of the people already done in the experiment. The solvent extraction is the most commonly used method for in the nuclear industry. Then all the reprocessing plant operates in our solvent extraction. In our nuclear plants, we will use the solvent extraction is the major tool for the separating any element of interest. The principle is, at a given condition, the distribution of any species in the two phases is constant. That is called the distribution law. And then you take something activity here, after certain time of equilibrium, you can see the activity measure again how much is reduced. From this I can see that what is the distribution coefficient. From that we can see the how to change the parameters to get the maximum efficiency of separation. Some examples I have given here. You see that organic phase, only that green color one is only active one in the aqueous phase. Then you make it equilibrium, then you see that after separation two phases, only the green color is only in the aqueous phase, only that other things are gone to the organic phase. From this that we can see that how much of distribution coefficients, how the separation efficiency, this all we can identify. Some examples I have given here. Suppose if you want to see the cesium separation by calyx 4 arene, you can take cesium isotope, cesium 137 is already heard, people are done in sodium iodide detector experiment. The same pencil source we are taken, the same something tracers you can take of cesium 137 and dope with that and do the solvent extraction. Then from that we can see what is the D value, what is the separation efficiency and other things. And same thing like ion pair mechanism. Suppose like one actinides if you take with having the charge of Z plus in the aqueous phase, the one it is gone to the organic phase, if you have something radioactivity here or you add something tracers, from these all mechanisms how it is getting extracted, what are the kinetics of extraction, everything we can identify. This is the already experiment we have done in the experiment number 4, the extraction of uranium by aliquot 336 is being extracted by using this aliquot 336, and because it is only uranium only forming the neutral complex and it is having more hydrophobic nature and it will go to the organic phase. Now this chloride is exchanged by using this molecule, and we already done in our experiment in the experiment number 4, the same example I have given here. Now if suppose you see this application of radio tracers in lanthanides and actinides separation study, in our reprocessing plant, what are the after irradiation the fuel in the reactors, if you dissolve it, half of the periodic table elements will be there in our reprocessing solutions. But suppose if you want separate one element of interest, suppose you want separate something americium for some other purpose, Now there are various researches being done to how to separate only the americium quantity. You see example I have given here. If you see the feed solution along with americium, there are so many elements will be there. Now they made a something optical fiber system where the selectively they will deposit our lanthanide extraction agent on these fibers, and then there will be one feed solution. Then when you are passing here, the cesium will be extracted, sorry, americium will be extracted here, and because of the process it will be migrated here, and they have something stripping reagent, and then selectively only americium will be getting out. That means you have something like a one tube, something imagine like this way, where we are passing the feed solution, and here I am using something continuously passing something stripping reagent, whatever from the feed solution to selectively americium will be separated and is coming here. This all process we can see by measuring the radioactivity emitting from the americium. You can see here the feed solution, americium is there. After certain time of that, the americium peak is disappeared in the feed solution, and again the receiver solution, americium only activity is there. We can see that how it is selective. Suppose someone wanted to see that how your process is selective only for americium. By using its radioactivity, we can see this type of applications. Okay. Then now I am going for the neutron activation analysis. Radio tracers and direct activity already we have done. Now we are going for something, activity will be induced in your sample. There are two different ways. One is by using neutrons and another one is the charged particles. The first I am explaining about the neutron activation analysis. Yeah, neutron activation analysis is the isotope specific and nuclear analytical technique capable of simultaneous multi-element determinations in diverse matrices. Because if you take anything sample and irradiate with a neutron beam or neutron either in the isotope source or in the nuclear reactors, then it will get captured by the neutrons and the activity will be induced, and we can determine almost like 70% of your periodic table elements can be determined by your neutron activation analysis. This technique is capable of determining as many as 70 elements in the periodic table, elements like sodium, potassium, up to uranium also we can determine. The application to many fields such as biology, geology, environment, forensic sciences, archaeology, medicine, these all samples can be done. Why I am going for this? Because something archaeological sample, their sample is so precise, it cannot go for anything like a non-destructive technique. Something the very old, some parts are identified. Then we want to see that the composition, and from this we can correlate what is the age of these parts. Then sample has to be very preserved very precisely. For that purpose you go for the NAA method. You can do the irradiation and you can measure the activity, because whatever the element change in this because of activity irradiation is very nominal. The isotopic composition or elemental composition will not change in this process. The sample can be treated as a preserved. There is no change in the compositional, because what are the activity we are inducing will be very traces compared to your matrix elements. We can say it is like a non-destructive technique. What is the principle in this? Actually already first lecture you have described about the stability region. Now by using the neutrons irradiation, we are just deviating from the stability region, because when you are injecting the something neutrons, it is deviated from the stability region. Again it will try to approach to the again to reach the stability region, and thus will apply something beta emission, and then along with that some gamma rays will also be emitted. From this we can, by measuring the gamma activity, we can see that how much of elements are there, how much of concentration is there in our sample. The principle here is same thing, that you are taking the target in the reactor, you take it and you are inserting the by neutron beam either from the reactors or some isotope source. Then when the neutron is captured, we are getting one compound nucleus, and then that will be get excited. Then when it is excited, on the spot it may be emit something gamma rays, that is called as a prompt gamma, because on the spot we are getting the one gamma ray, that is called prompt gamma. Suppose when you are disturbed from the stability region, then again it will emit something beta minus something particles. Then it will take maybe some with some certain off lives. Then we can measure offline, that is called normal NAA. If you want to see the direct, that is called prompt gamma neutron activation analysis. Okay. Like the principle, same thing I explained here. This is a neutral molecule. When you bombard with a neutron, then you will the compound nucleus have the different excited states, and it will has to come down to the immediately to the ground state of compound nucleus by emitting different gamma rays. If you are measuring this, is called as a prompt gamma neutron activation analysis. after certain lifetime it may be changed to beta emission, something like that. If you are measuring gamma of this is called as a neutron activation analysis. Okay. What is the activity you are getting in the neutron activation analysis? The formula is, because when I am targeting, it all depends on the number, how many number of atoms you are taken in the target, that is represented by n, and when I am taking bombarding something, there will be something probability of reaction, that always represented by sigma, that is the capture cross section of your element of isotope of element, and then pi is the flux, means per unit area how many neutrons you are bombarding, that the flux. And during this irradiation itself, some of the particles may be decay, that is called saturation factor, that is represented by 1 minus exponential of lambda Ti. I is the time of irradiation, and then it is a cooling up, mean it's not like that something you have done the irradiation, immediately you can measure the something activity here, maybe something cooling will be there, that decay corrections also will be incorporated here. Then from this we can see that how much of activity are induced, and then when you are measuring the CPS, again you have to see that what are the efficiency of your detectors, and then from this we can, what is the gamma ray efficiency, the gamma ray efficiency, from this we can see the what is the concentration, because basically you are getting something counts, from that we have to correlate what is the concentration. By applying these all parameters we can use quantify what is the element of interest in your samples. The experimental methodology is the collection of a bulk sample, what the sample you are taking, and then preparation of sample for irradiation, depending on your requirement and what the beam size and what the conditions for taking into the reactors, you have to prepare according to sample preparation. And of course, because these all are relative methods, the activity it is whatever is coming, then you have to simultaneously same way you have to make something standards. From the standard activity we can correlate the concentrations, the irradiation media source like reactor or isotope source, the samples for counting, then activity measurement like gamma spectra, and then spectral analysis, the concentration calculations as the formula is given in the previous slide. Then also evaluation of uncertainty, that will give more confidence in what the values you are giving than the interpretation of your results. The once you are identified what is the element concentration, from this maybe that why the concentration changing, and that from this what you want interpretation of results can be done from this. There are some of the cases like arsenic or selenium. It's not only the total concentration, there maybe we require something chemical species. That means what is the nature of your sample is there, like arsenic 3 or arsenic 5. In the case of selenium, there are some of the elements like arsenic, mercury, chromium, lead, selenium. These are the toxic nature in the elements. Anything water analysis you have to do, groundwater analysis, sample analysis has to be done. We can go for the total concentration. Some cases maybe you require something chemical species, you have to do something chemistry here, you have to separate some by using something methods like arsenic 3 or arsenic 5, and then go for the new NAM methods, we can quantify. The total for arsenic concentration determination, just take some arsenic sample, go for the irradiation, you will get the arsenic 75 to arsenic 76, and it will emit the one beta followed by one gamma, that is 559 keV. By using these intensity measurements, we can see that how much of arsenic is there, and there is a specification for WHO, arsenic should be less than 10 nanograms per ml, that means 10 ppb, then we can see that what is the total arsenic concentration. But if you see the toxic nature, all they have the arsenic have the different species like arsenic 3 and arsenic 5, all are not the same way it will affect your health. Then if you want to see the further which is the affecting more or which is the more concentration in your sample, you have to do something separation by using something ion exchange method, something like that. Then also we can see that what the chemical species are present. You have to see something chemistry followed by NAA, that's called chemical neutron activation analysis. From this we can see that how much of arsenic is 3 or 5 are there. Okay. Suppose in the PGNAA, it is a complementary to NAA, because when on the spot where you are doing irradiation, there itself gamma ray will emit, and then we have to measure from that, and then from this we can do the what are the calculations we can do, how much we can quantify, how much of element is there. This all depends on the what the abundance of gamma, the abundance of your gamma, what is the neutron flux is coming, and this all parameters we have to apply, and then we can see the how much of element is there. The typical setup whatever I am showing here, you take the beam from the reactor and you take the sample here, and then you have to, what are the activities you are induced, and the prone gammas are coming on the spot. The simultaneously we have to measure the radioactivity gamma spectrum, and this is the detector we are using. It is simple HPGE followed by some BGO detectors will be there, because when I am doing irradiation there are multiple gammas are coming, the resolution may be, because of Compton scattering the spectra will be more complex, then accordingly they have to change the detection. This is the setup they are used for the measuring the prone gammas. Okay, the some important features of PGNAA, the advantage is the ability to determine the light elements, because if you go for the lighter elements, the simple NAA cannot be done, because as Savichachi Patra already explained in the first or second day, that in the lower region, if you see the binding energy for nucleon is changing very drastically, the on the immediately the reactions will happen, it does not have anything lifetimes there. Then we have to measure online activity only. In that case, the PGNAA is the best method. If you go for something higher mass numbers, then you can induce the activity having certain lifetimes. We can go for offline measurement, that is NAA. If you want to go for any lighter elements, the PGNAA is the best method, and as I mentioned, it is all non-destructive nature for all these NAA method. If you want how the sample should be like the reserve, very precise, then we can choose one of the method is the PGNAA or NAA to solve your problems. Of course, something isotopic analysis is also possible, like something sulfur, silicon, nickel, something elements. Some one example I have given here. Suppose if you want to determine the boron, and suppose in the liquid sample or something like that, maybe the concentration may be very too low, then we have to do something pre-concentration and then go for the PGNAA. Then we, from this counts we can determine what is the boron content, even a 0.5 ppm also can be determined. Okay, because we are doing something pre-concentration followed by PGNAA, even very low levels of boron content can be determined in this method. Just spectrum I am showing here. These are the calibration plot, but I am saying that when I am doing something measurement, I have to do the calibration, because signal to your concentration correlation is applied. And one of the example is the PGNAA. Now the Ukraine Russia maybe war may be over, we hope something in the future it may get over, but in this war maybe they will put so many land mines in your fields. Then like for example I will say that the Vietnam war is maybe completed in around 1980s. Now around 20 years it took to identify where they kept the mines. Now for that purpose, like a PGNAA, the non-destructive technique is one of the best example, because they can take the portable gamma with this neutron source, and from the what are the activities getting from the mines, they can identify what is the mines location. That is the one of the best example of application of PGNAA, and it is the one of the highest funding for this technique by our UN, United Nations, to determine the landmine detection. Maybe the same application may be required once again after the end of this Russia and Ukraine war, because they will keep so many landmines to give the effect to something the opposite person. After the end of war, maybe our own people maybe also get affected with that. They have to identify what are the landmines. The one of the best application is the PGNAA for this purpose. The ion beam analysis. Now we are going for entering to the, we are inducing the activity by using your ions like charged particles. Now in this case, when I am saying the charged particle, there is always one Coulomb barrier will be there. Coulomb barrier will be there, then we have to accelerate your charged particles such that it cross the Coulomb barrier and interact with your element of interest. There are so many approaches are there. I am just taking the ion beam here. When I am bombarding here, if you something do the nuclear reaction there, then gamma ray will be emitted, some inducing the activity gamma ray. If you are measuring the gamma ray, then we call particle induced gamma ray analysis. And in this process, like excitation and ionization is the normal process of any energy deposition of radiation. Now something ions maybe get excited, elements will get excited, that at that time it will emit the X-rays. If I am measuring the X-rays, that technique is called particle induced X-ray emissions. Now as the Rutherford had done the experiment backscattering, now if you are using target is a lighter element and your target is, the projectile is lighter element and target is heavy nucleus, then if you will bombard it may get backscattering. From this we can identify that what the element present is there in the sample, and then what is the concentration from that. If I am using the backscattering, that is called RBS. Now if the nuclear reaction is happening, means if you are projecting with some energy, After losing some energy, it cross exactly matching with your Coulomb barrier. When the resonance energy will appear, then the reaction is happening, nuclear reaction is happening. In this process, something gamma ray will also emit. If I am measuring that gamma ray, that is called as a NRA. And if you are anything recoil, something when I am bombarding with one projectile, the target maybe can have something recoil energy. If I am measuring that, that is called as the recoil nucleus. The transmitted particles, from that we can see the what is the thickness of your sample plates or something like that. There are so many ways by just bombarding your particle, charged particle acceleration. Then what the way you are approaching, there are different techniques you call like NRA, PZ, PIXI, RBS. There are all other different ways of getting analysis, radioanalytical techniques. Okay. The simultaneous determination of isotopic composition and total concentration of boron by 1 PG. So, one of our colleague from radiochemistry division has done the not only boron total concentration, he can also see that how much of isotopes. Generally we will go for like mass spectrometry, we can go for something like a PG method, particle induced gamma ray emission. We can see the what are the isotopes also, the some of the examples only I am mentioning here. Then the nuclear reaction analysis, the one of the ways that now everyone is talking about something like hydrogen energy. Now when hydrogen is charged onto your as a storage material, if you want to see that whether its only surface is absorbing, whether it is going to the inside or not, if you want to see anything depth profile of your charged particles, storage material, then we can see the nuclear reaction analysis is a very useful for hydrogen and a very good depth resolution, the sensitive to one element at a time. The main principle is here, if you see something like a hydrogen, if you are taking as a projectile as a fluorine 19, and then we have the reaction after the one reaction, it is forming helium 4 and O18 gamma ray, but every reaction have some resonance energy. Okay. Now you accelerate something energy, particular energy of fluorine 19, when you are bombarding, first it will lose some energy up to reaching the resonance energy, then it will capture the reaction. Now by knowing that how much of energy lose for a unit distance, and then from the resonance energy we can see the depth profile and as well as your concentration also. The examples I mentioned here, you see here this is the depth, and from that gamma's energies where we are getting, from that we can see the what is the depth profile of hydrogen, and we can see the what is the concentration also. Okay. The E minus E resonance and the dE by dx, the energy of what the charged particle we are accelerating minus your resonance energy divided by dE by dx, the per unit distance how much energy is losing of this charged particle. From this we can see what is the depth profile of hydrogen. This is one of the example only I am mentioning here. Here they are taken as the N15 as the projectile, and every reaction have its own resonance energy. Depending on your application, we have to choose which particle you want for the inducing the radioactivity. The hydrogen profile in silicon implanted on the by using oxygen 16 centimeter square 14 keV. This is one example I wanted to share to see the depth profile of hydrogen nickel silicon sheet. The ion beam analysis, not only for chemical analysis, it can be applied for the material science like archaeology, environmental science, physical, chemical. There are enormous applications are there. You can collaborate with any BRC or any other institute in case if you require any this type of analysis. With this I will conclude. Thank you for your attention. As I mentioned earlier, my aim is not to make you expert. I just want to give that something flavor of application of radioanalytical techniques. In the future, whenever you face something problem in your scientific career, you can have something thought about that we have one more option like this way. That is my aim. I don't know whether I succeed or not, but that is what I want to say. Thank you. I can answer any questions. If
Thank you, sir.
Yes.
So whether this ion beam analysis technique is a non-destructive or destructive kind of?
It's a non-destructive nature, because see, whatever the cross sections you use, if you compare to total elements present in your sample and what you are getting induced, activities induced very small, we can treat them as a non-destructive technique.
Second question is it possible to develop the CCD based detectors?
We want that CCD based.
CCD based, yes.
Okay, but finally you require something energy resolution that may not be possible with your CCD one, no? Because photographic plate you will get only image, from that we can see the how much of concentration is there. The energy is not possible. I don't think so.
Any more questions?
Okay, thank you. Thank you very much.
Thank you. Now I welcome Dr. K. Suresh Garu for the feedback on this session.
Good morning, one and all. I must thank the organizers for giving me this chance to propose vote of thanks for our today's speaker, Dr. P.S. Ramanjaneyulu Garu, on applications of radio analytical techniques in research. Once again, thank you, sir, for giving nice talk and very clean and more enlighten our students. I once again thank you very much, sir. Thank you.
Yes. Sir, I have a question actually. So what is the portability of these instruments? Like some are really heavy that if you want to do some analysis, we have to come to you.
No,
Yeah,
see,
yes.
some of the gamma detectors
Yes.
with Peltier cooling also is a carryable.
Okay.
You can carry wherever you want some field applications.
Yes.
It's not like that always it is bulkier.
Yeah, yeah.
Yeah.
Yes.
Suppose in the case of sodium iodide, nothing is required.
Yes,
you
yes.
carry easily.
Yes.
But you have to see that application.
Yeah,
Resolution, that's just your
Yeah,
application
yes.
size.
Particularly for material science and these things, we have to come to BARC because we need neutron source and all those things.
See, that all depends on some isotope sources are also available.
Yes.
At around 20 years back, we have a facility in our Andhra University also.
Yes, now it's
In
not.
the nuclear
Yes.
physics department. At present, I don't know.
Now it's
But
not
in the
there.
case
Yes.
of you require higher flux, maybe you have to come to the
Yes.
reactors. But otherwise, isotope source can be used.
So portable neutron sources are there.
Yes, it's available.
Okay.
In Andhra University nuclear physics department, it is not available. But 20 years back, it is available.
Thank you, sir. So now we will go for a tea break, and I request all of you to come back sharply by 11:15. We'll start next session.
Thank you, sir, for giving this opportunity to introduce Dr. Tapas Das. Dr. Tapas Das is presently working at Radiopharmaceuticals division of Baba Atomic Research Center, Mumbai. He had joined DA in 1998 after completing his post-graduation in chemistry and 1-year orientation course in nuclear science and in engineering from the BRC Training School. He had obtained PhD from University Mumbai in 2004. His research fields of interest includes production of radioisotopes and development of radiopharmaceuticals for diagnostic and therapeutic applications. He has received several awards which include Professor J. Anikar Best Thesis Award, Tarun Datta Memorial Young Scientist Award, DAE Young Scientist Award, DAE Scientific and Technical Excellence Award, multiple DAE Group Achievement Awards, etc. He has served as a technical cooperation expert and consultant of International Atomic Energy Agency, Vienna, Austria. In multiple occasions, he is a professor and recognized PhD guide of Omi Baba National Institute, Mumbai. He has published around 110 research articles in various peer-reviewed international journals. He is a fellow of Maharashtra Academy of Sciences and editor of journal Applied Radiation and Isotopes, published by the elsewhere. He is a regular ad hoc reviewer of more than 25 reputed international journals published by ACS, American Chemical Society, and RSC, and elsewhere, Wallis, Sprenger, Bhentan, Hendwan, etc. So with this very brief introduction, so I am inviting Dr. Tapas sir, please to come and give an our interesting talk on radiopharmaceutical analysis. Thank you, sir.
Change. उतारा है change. Am I audible till the end? Yeah, thank you, thank you. Okay. Thank you, Dr. Naidu, for your kind introduction, and good morning to all of you. So, as you can see, the title of my presentation is Application of Radioisotopes in Healthcare. So, last 3 days you have heard a lot about radioisotopes and radiation, and just now my colleague Dr. Sitaram, he has given a very nice presentation of how the radioisotopes can be used in, I say in science, not in chemistry. And now I will try to show you or try to explain you how these radioisotopes can be used in healthcare. So, let us start from a very simple thing. You know all these things, I know. What is isotope and what is a radioisotope? So, as you know that the isotope is nuclides having fixed number of protons, but variable number of neutrons. This you have maybe read in your 8th or 9th standard, and here I have given one example. As you can see that carbon 12, carbon 13 and carbon 14, they have all 6 protons, 6 electrons, but differ only in their number of neutrons. Now, when this isotope becomes radioactive, they emit some kind of radiation, we call them radioisotope. And if you look in the literature, you will see there are around 3000 isotopes, and out of which only 250 roughly are stable radioisotopes. So, all remaining things are radioisotopes, and majority of the radioisotopes are man-made, that is artificially produced. We produce it using the reactors, cyclotrons, etc. That maybe tomorrow when I will be telling about the production of radioisotopes, I will try to cover. So, this radioisotopes has lot of uses for societal benefits. As you can see, I have tried to list here biomedical applications, that is it is used for the diagnosing the problem in the human body, treatment of different types of the diseases, and also for sterilization. So, today I will cover this part, and I think sterilization tomorrow my colleague Dr. Atanu will cover how the radiation can be used for sterilization. It is used in industry and hydrology like radiography, tracer, gauging, radiation processing. Again my colleague Dr. Atanu will present this tomorrow. Food and agriculture, food preservation, tracers and mutation. I think again Atanu will tell something, and maybe Dr. Daniel Babu has also covered maybe yesterday to some extent, and research which already my colleague Sitaram just covered. So, I will concentrate here how these radioisotopes are used in healthcare, that is for the biomedical processes. So, radioisotopes in healthcare is used in 3 different ways. One, for diagnosis of diseases, that means whether the human body is malfunctioning, we are just trying to detect that, not to treat that. Second one is therapeutic, that is when you are trying to treat that problem, and third one is radiation processing. This part again tomorrow Atanu will cover. Now, I will introduce a concept of radiopharmaceutical. So, what is a radiopharmaceutical? As the name indicates, it is basically a radioactive pharmaceutical. Pharmaceutical means that is a drug what you take when you are not well, and when we add a radioisotope with it, that is called radiopharmaceutical. So, by definition it is a special class of radioisotope based preparation which is suitable for administration in patients. So, its quality is so good that you can administer in human, and it is either used for diagnosing the diseases or for the treatment of diseases. So, it can be of 2 types. One is called diagnostic radiopharmaceuticals, other one is called therapeutic radiopharmaceuticals. Sorry. So, now what is a diagnostic radiopharmaceutical? So, as the title suggests, it is a preparation, rather radioactive preparation, which is used to find out whether there is any malfunction in the human body. So, let me explain how it works. So, I think you are very familiar with the X-rays, either you or some of your friends or colleagues or family members have sometime taken the X-ray. What happens? There is a X-ray source, X-ray comes out from this source, passes through the human body, and you detect it by using a X-ray film, or detector, mostly X-ray film, and you present that X-ray film from the radiology department to a doctor who sees the X-ray film and tells whether the bone is broken, whether there is a congestion in the lungs and so many other things. It was extensively used during the COVID period. Now, in radiopharmaceutical, there is basically no source. Here what we do, a radioactive preparation we make and inject it in the patient's body directly. So, here the source is patient himself or herself, because we have injected the radioactivity in the patient's body, and due to the radioactive decay, radiation will come out from the patient's body, which is detected by using the detectors, and we get this kind of the images from where the doctors who are learned doctors of nuclear medicine, they can get a wealth of information. So, I will try to explain some of these things as we progress with this presentation. Similarly, for the therapeutic radiopharmaceutical, it is a radioactive preparation where again some radioactivity is incorporated, by the intention is this time not to detect the disease, but to treat the disease, that is to cure the disease. And therapeutic radiopharmaceutical is predominantly used for the treatment of cancer, though it has some non-cancerous application, but majority it is used for the treatment of cancer. So, now let us look about the world scenario before we actually come to actual subject. So, there are around 40 million patients who are benefited annually from the nuclear medicine treatment. This is the global statistics, and over 1 lakh patients are diagnosed and treated with medical radioisotopes each day. And you can see here, though by the term radioactivity or radiopharmaceutical, it always we think it is a cancer. The major use is not for the cancer. The major use of radiopharmaceutical is in nuclear cardiology to detect the heart diseases. I will try to explain how it is used, followed by oncology, that is for the treatment of cancer, followed by thyroid, and this is the trend in 2024, and you can see next 5 years the trends almost remains the same. So, its major use in nuclear cardiology, followed by the detection and treatment of cancer. And here I have tried to show that any body organ you take, any function you take, we know the radiopharmaceutical, what to use and what information we can get. This is very well known, standardized at this moment. So, here the uses all over the world, you can see majority of the things are used in the America. Almost 50% of the radiopharmaceutical is used in North America and then Europe, and this is the scenario of the Asia Pacific. So, it may be world's 10 to 15%. So, total Asia uses, though we have the major population, we use only 10 to 15% of the world use of nuclear medicine in India. And again, if we look carefully in the Asian region, you see here majority are used in China, then Japan, and this is India. So, just world's 1.5 to 2% of nuclear medicine we use, though our population is world's almost 14 to 15%. So, we have a lot of distance to cover. So, at this moment there are around 10,000 hospitals in the world who uses nuclear medicine, and 90% of the procedure is for diagnosis only 10% minuscule is for the treatment. And out of this 90%, 80% of this nuclear medicine procedure and 85% of the diagnostic scan are based only on one isotope, that is 99M technetium. M stands for metastable, I think you know by this time. So, this is the isotope which is the bread and butter of the nuclear medicine industry, because 80% of today's use, not only in India, all over the world, is based on 99M technetium. Why? I will try to explain tomorrow morning when I will be telling about the isotope production. Now, coming why we need radiopharmaceutical. Now, when there is a malfunction in the human body, when there is some problem, a patient is complaining, doctors need to know why he or she is complaining, what is wrong inside. But unfortunately, our human body is opaque. You cannot see from the outside except the few organs. So, in medieval, when the people were complaining, if it was really serious, the only option was to open cut open the patients. That is of course not a very good idea, and in present day we cannot think of that. So, we have now, thanks to science, thanks to hard work of lot of scientists, we have several good techniques. Like already I have explained, X-ray, ultrasound, computer tomography, CT scan, that is again where you use the X-ray source, MRI, magnetic resonance imaging, which works on the principle of NMR, nuclear magnetic resonance spectroscopy. So, we have so many techniques. Then really do we need a nuclear medicine imaging? Do we really need radiopharmaceutical? Because you are of course you are using some radioactive preparation, injecting such preparation in the human body, and we all know that radioactivity is harmful. So, why we need to inject a harmful substance in the patient's body when we have so many other techniques, and they produces beautiful images. As you can see, this is an X-ray, this is a CT image, this is an MRI image, this is a MRI and CT image of brain. So, very beautifully it captures the brain anatomy. Then why we need to do the nuclear medicine imaging at all? Why we need to inject radioactivity in the patient? Now, if we look X-ray, USG, CT, MRI, all gives only the anatomical information. It takes a picture. It does not take part in the biochemical process. So, it is just a photograph, beautiful photograph. Now, nuclear medicine scan that we do with the radiopharmaceutical is the only method by which we can do the functional imaging. Now, what do we mean by functional imaging? Say whether heart is pumping the blood properly, whether the blood is going to all the cells of the heart, whether kidney is filtering properly. So, all this information you cannot get from here, only you can get if there is a structural abnormality in these organs by the other methods. Now, why this radiopharmaceutical has that advantage of functional imaging? Because it is taking part in your biochemical process. It is a preparation which are injecting in the blood, and it is taking part in the biochemical process. So, we can have the other information, and we use these techniques as complementary techniques. As if you concentrate here, so this is a brain image what we obtain from the radiopharmaceutical, and you need not be a doctor to tell these are far better images than this. Now, then why we need this? Because you can get the functional imaging. Again, it will be more clear when I go to the subsequent slides. Now, I will try to explain this. So, this is the thyroid. Thyroid, you know, thyroid disorders is very common, particularly in females. 80% of the thyroid disorder patients, including thyroid cancer, are basically females. So, we need to know where is the problem. So, what we inject is 131 iodine, that is an radioisotope, because you know our thyroid has T3 and T4. There are two hormones, triiodothyronine and thyroxine, which have the iodine. So, if we inject the radioactive iodine in the body by biochemical process, by body's own mechanism, it accumulates in the thyroid gland. And if we concentrate here in this here, you can see that iodine is a cold nodule, iodine is not getting accumulated here. That shows there is some issues here, this thyroid gland is not working. Now, doctors can take the adequate steps. Now, it will be more clear here, this is a heart image. So, this is a patient, this has been imaged with 82 rubidium, one of the radioisotope. You can see here the patient is in rest, patient is sitting, and we have injected the rubidium chloride in the patient's body, of course radioactive, and then we have taken the images. What you can see? Fantastic. These are the heart muscle, blood is going everywhere. Now, what we ask the patient to run in the treadmill to create some stress, that when you are in stress, how your heart is functioning. And you see, when we have taken the image in the stress condition after he or she runs in the treadmill, and you see here, you see this circle is not completed. That means what? These muscles in the heart, those are not, they are not functioning in the stressed condition. So, blood flow has already reduced there, it has not adequate blood flow. This condition is called ischemia. This is called ischemic heart. And there is another thing that is called infarction, when there is no blood flow at all. So, if a cardiologist see this patient, he or she can take adequate action, give the medicine, because already these cells are not dead, but they are not functioning properly. The blood flow has already reduced, which is viable only when he or she is under stress. So, these kind of the information, this is we call functional imaging. These kind of the information you cannot get from the X-ray or CT. So, you need the nuclear medicine imaging. Here you see another example. This is a whole body image of a patient who is having the cancer. Now, what happens when the cancer goes to the advanced stage? It causes metastasis. What do we mean by metastasis? Means when the cancer has spread from its origin. Say it may be a cancer of liver, it may be a cancer of breast, it may be a cancer of prostate, but it has spread in the body. So, doctor need to know when the patient come, doctor need to know what is the stage of the cancer patient. You have heard stage 1, stage 2, stage 3. What does it mean? Because we need to know how much cancer is spread, because the treatment depends what is the stage of the patient. So, if it is a stage 1 cancer patient, if the cancer is located in a particular place, you can do the surgery, that is the best thing, or maybe chemotherapy. But if it is in the advanced stage, you cannot cut the patient in multiple places. You can do chemotherapy, and you know what is chemotherapy, you know that is a poisonous chemical you are injecting to kill the cancer cells, and after a certain doses you cannot further give chemotherapy because it is very difficult to tolerate. But how they will know, or whether when they are treating the patient, whether it is working, whether the cancer burden is reducing. So, they need to do this kind of the imaging. And here if you look, see there are some extra points you can see here. I do not know whether it is visible. I think from this screen you can see it properly. You can see here there is some extra dots in this region here, at least you can see. So, these we called hotspot, that indicates the radio tracer has accumulated more there, more radio tracer has been accumulated, that indicates that cancer has spread in the body. I will show further examples. So, I am just showing you how the radiopharmaceutical can help in treating the patients. Last example, so this is the image of a child. See, the radiopharmaceutical is so safe that even we can use in few months old child also. So, you can see this is the kidney images. We have injected some radiopharmaceutical, and you can see the tracer is going in one of the kidneys. So, left kidney is basically, right kidney is basically not working because the tracer has not gone there. We have injected some radioactive preparation in the patient's body, and if both the kidneys are working, both should be equally hot. But you see these two kidneys, the right side kidney is not hot. That indicates there is something, that blood is not flowing or the kidney is not functioning properly. There may be some obstruction, there may be some blockage, but this much without opening the patient we can tell that his or her right kidney has some malfunction, and if we go further we can tell what is the malfunction. Now, so now I think you are a bit convinced, yes, radiopharmaceutical is required. In some cases we need to inject it in the patient's body to get more information. Now, what is a radiopharmaceutical? How it looks like? So, basically radiopharmaceutical has two major parts. One part is called the carrier molecule and other part is the radioisotope. Now, what is the carrier moiety? Carrier moiety may be a peptide, may be a hormone, may be a biomolecule, may be a small molecule which takes this whole preparation to the target. What is the target? Target may be a tumor, may be a receptor, may be the cancerous cell, may be the antigen, etc. So, this has the property to bring it to the target cell. So, to be more clear when we go further in this presentation, and with that we add a radioisotope. So, when it goes to the target, it carries the radioisotope with it, and if the radioisotope is diagnostic in nature, then we call it a diagnostic radiopharmaceutical. If it is therapeutic in nature, we call it a therapeutic radiopharmaceutical. Now, what is a diagnostic radionuclide? I will explain that it emits a gamma radiation. It may be a gamma emitter or it may be a positron emitter. Why we need gamma? Because gamma has a longer range, you know that thing by this time, low LET, longer range. So, it comes out of the body and interact with the detector. What we have done is that we have injected the preparation in the patient's body. So, what radiation will come out, what I have shown, it need to interact with the detector. So, it should have certain range. If I put the alpha or beta, the range is very, very low. So, they will not come out of the patient's body, they will be attenuated within the patient's body. So, they will not interact. So, we need the pure gamma emitters or maybe the positron emitters. Why positron emitter? I will come to that. And for therapeutic one, we need alpha or beta because they have the high LET. This time our target is to kill the cancer cells. And please note that in a radiopharmaceutical, they has no pharmacological effect. What do we mean by that? So, say you have a headache, what do you do? Or you have a fever, what you do? You go to market, take a crocin or paracetamol, 500 milligram. You pop it and after some time you get the relief. So, here the response comes from the drug, that paracetamol moiety. In radiopharmaceutical, whatever the efficacy we see, it is not from the drug, it is from the radioisotope part. The reason is here the drug quantity used is very, very less, maybe microgram, sometime even in nanogram level. So, it cannot have any pharmacological effect. So, whatever relief we are getting, whatever the treatment we are doing, it is basically due to the radiation which is coming out from the radioisotope. And the role of this drug or this carrier moiety, what we call commonly, is just to take the radioisotope to the organ of interest. Otherwise, if we just inject the radioisotope, it will go anywhere and everywhere, which we do not want. We want to make it target specific. So, if we want to treat a kidney disease, I want it to go majorly to the kidneys. If I want to treat something heart, I want to see whether there is any malfunction in the heart, I want it majorly to go to heart. It cannot be 100%. So, how will achieve this? This is achieved by this carrier moiety, and whatever the efficacy you are seeing, this is due to the radioisotope. So, basic difference between a drug and radiopharmaceutical, or rather pharmaceutical and radiopharmaceutical, is that this radiopharmaceutical has no pharmacological effect. Its effect is coming only from the radioisotope. Now, this I will come tomorrow. So, I will skipping this, how we produce the radioisotopes. Now, see, these are the important radioisotopes what we use for the diagnosis, that is for knowing whether the patient is having any problem in the body. And I already told the majority of the things comes from 99M technetium. Majority of the radiopharmaceuticals are based on 99M technetium. It is almost 80% is used. There are some other isotopes, but their use is comparatively much lesser. So, these first 5 are basically produced. These are basically some are reactor produced, some are generator produced, some are cyclotron produced, and these are SPECT radioisotope. SPECT means single photon emission computed tomography. These are basically the gamma emitter, and these bottom 5 are the PET isotope, which is called positron emission tomography. I will come to that. They are positron emitters basically, they are pure gamma emitters, and in the positron emitter, this is the maximum used is fluorine 18. Now, I told that there are 2 parts, one is the carrier moiety, other one is the radioisotope. So, these are the different carrier moieties. So, these are designed so that it goes to a particular organ. I will not go to the details, but this is we called HMPAO, hexamethylene propylene aminoxime. This is used when you label with technetium, it forms this kind of complex and it goes to brain. It is used for the brain imaging. MEV, that is methyl isobutyl isonitrile, this is for heart imaging. Tetraphosphine, this is also for heart imaging. Like EC, ethylene cysteine dimer, that is used for the kidney imaging. Now, why it goes to kidney, why it goes to lungs, why it goes to heart, this is beyond the scope of this 1 hour 15 minutes. So, I will not go to that, but these are made with some logic which takes the full preparation to the, say here it is brain, here it is heart, here it is kidney, this is also for kidney. So, there are some specific, these are basically the carrier moieties, some examples of the carrier moieties. Now, how we make the radiopharmaceutical? This is the whole process. So, we take the target, this maybe tomorrow I will be explaining in a better way. that is a stable say salt or maybe metal, and we put it in the aluminum can, seal it, send it for reactor irradiation. So, once it is irradiated, it becomes radioactive. So, these are lead shielded casks. We put the irradiated target in the lead shielded casks and send from reactor to the radiochemical processing laboratories. Here you can see our radiochemical processing laboratories and my colleagues who do the radiochemical processing. So, once it is radiochemically processed, so radiochemically processed means you have to make it a particular form, chemical form, so that it can be used for the preparation of radiopharmaceutical. So, after that we dispense it and send it to BRIT, pack it and send it to BRIT. BRIT is our commercial wing of Department of Atomic Energy, known as Board of Radiation and Isotope Technology. So, they send it to the hospitals, or in some cases we make radiopharmaceutical formulation, that is we add it with the carrier moiety, do the quality control tests and again dispense it, pack it, send it to BRIT, and from BRIT it is sent to different hospitals. So, this is the total cycle of preparation of the radiopharmaceutical. One of the major problem with the radiopharmaceutical is that you cannot prepare and keep it in the shelf, because it is continuously undergoing decay. And for healthcare, whatever the isotope is used, they are all short-lived isotopes. So, just like in pharmacy, you go and ask the pharmacist, you please provide me this medicine, he or she takes out from the shelf and give it to you. But here it is not possible, because these are a very limited shelf life. So, you have to prepare sometime on daily basis, sometime on weekly basis, depending upon the half life of the radioisotope, and give it to the patients. Now, see, we have several fridge dried kits supplied by the Department of Atomic Energy for the healthcare applications. What do you mean by the fridge dried kits? Fridge dried kits is a preparation where we have mixed everything, all ingredients, its pH is fixed, everything is fixed. What the doctor or the hospital people has to do, they have to just mix the radioisotope with this, heat it sometime or sometime keep it at room temperature for some time, and your radiopharmaceutical will be ready. As I told that we cannot produce all the radiopharmaceuticals in Mumbai and send it to all over India, it is not possible, because the major radioisotope which is used is 99M technetium, which is a half life of 6 hours. So, even in a day it will be almost over. So, we cannot make it in BRC or BRIT and send it here. So, what we do is that we make the fridge dried kit where every or all ingredients is readily put there, and these fridge dried vials are supplied to the hospital. So, hospital take these fridge dried vials and store it. They have a shelf life of 6 months or at least 1 year, depending upon the kits. So, what they do is that they just take the radioactivity like technetium M, which is obtained from a radionuclide generator. I do not know whether the concept of generator has been told. Yes, so we are doing some, you have told? Yeah. So, generator you know, otherwise tomorrow I will explain. So, you can take the short lived activity from the generator, which is kept in the hospital. You put it in the kit, wait some time, do the QC, which is simply a paper chromatography majority of the time, and it is ready. If it passes QC, it is ready for the injecting to the patients. So, these are the different types of fridge dried kit, and you can see their applications. I am not going to the details, but you can see almost every organ we are covering, from kidney, liver, bone, hepatobiliary is liver, myocardial is heart, sentinel lymph node, this is for brain, dopamine transporter. So, almost every organ is covered, and these are regularly supplied from the BRIT, Board of Radiation Isotope Technology. If you are interested, you can just go to the BRIT website, www.britatom.gov.in, and you can have, I have taken from BRIT website only. So, you can get it from all the information from there. Now, fine, we have prepared the radiopharmaceutical, it is ready. Now, we have injected into patient. Now, what after that? So, what we do is that we ask after a certain time, we ask the patient to lie down in these beds. So, you can see these are the called gamma cameras. So, patient will lie down here. This is a single head gamma camera. So, whatever the radiation will come out, it will be detected by this detector. There is some detector here. You know what is detector, because we are doing practicals and already radiation detection has been taught. and this is a dual head gamma camera. So, it will detect from both the sides. See, patient is lying, I told that patient himself or herself is the source, because we have injected radioactive preparation in the patient's body, and whatever the radiation is coming out, it is detected by both the detectors. So, this technique we called SPECT, single photon emission computed tomography, and what we get is this kind of the images which I have already shown. Now, before I explain this image once more, so let me tell you what is computed tomography. I do not know whether you have idea or not. See, tomography is a word which means when you are taking the images slice by slice and reconstructing it by using a computer algorithm to make it 3-dimensional. That is the reason computed, we call computed tomography. So, what is CT imaging? It is the same thing. Say I want to know, a doctor want to know how a patient's heart is or kidney is functioning. So, what they will do? That they will use X-ray, just normal X-ray, it takes only 2-dimensional, you will get in a plate. It will take X-rays in all the slices possible from all the angles, and then the computer algorithm will use those information to construct a 3-dimensional image. That is called computed tomography. And when the source is single photon, that is gamma radiation, we call it SPECT, single photon emission computed tomography. Now, let us, I have shown you this image. Now, let us look carefully what the doctors can have information from these images. So, this is a normal person, just like me, just like you. So, if you, and radiopharmaceutical you have injected is 99M technetium labeled MDP, methylene diphosphonate. It is a bone imaging agent, and this is the used very heavily in the nuclear medicine center, because when a patient comes to a doctor, doctor first need to know what is the stage of the cancer. So, first they ask the patient to do a MDP scan. Now, it is a phosphonate. So, you know our bone has lot of calcium. So, due to its attraction, calcium and phosphonate, it goes to the bone. Now, this is a normal, you can see all the skeleton, rib cages, everything. Now, come here, this is a prostate cancer patient, a male patient having prostate cancer, and you can see here the extra dots here, near rib cage here, you can see these extra dots. That means what? The tracer is going and accumulating there more. So, bone turnover is more there, that indicates the cancer has spread in multiple locations, that is the patient is having metastasis. So, these kind of the patients are very difficult to treat by surgery, because you cannot do surgery where you will cut the patient. Now, this is another image, similar kind of image from a breast cancer patient. So, you can see here again there are lot of additional uptake, even you can see the shoulder joints here, you can see the extra dots, that indicates basically again the cancer has spread throughout the body, and then doctor can take the adequate measure, tell what type of treatment will be useful or whether at all it will be useful. So, for this, these are regularly done in nuclear medicine centers. Now, coming to, this is about SPECT, single photon emission computed tomography. Now, I am coming to the other technique, that is called PET, positron emission tomography. Maybe you have, many of you heard that the cancer patients are undergoing PET scan, or maybe for Alzheimer patient. So, what is PET scan? So, it is a positron emitter we inject in the patient's body. So, what happens when the positron comes out, it meets with an electron, because it is a very short lived, almost unstable thing. So, it meets with the electron and emits 2 gamma radiation of 511 keV each at 180 degree apart from each other, and these are simultaneously detected by the 2 detectors. So, this is called positron emission tomography, and it gives an image which is far higher resolution than the SPECT. Why? Because the detector only takes those gamma radiation into account which are simultaneously detected at 180 degree apart. All other things which are coming out, they just reject it as noise. So, here the signal to noise ratio is much higher compared to SPECT, and we get a far improved image. So, as you can see here, so this is the image of human brain. So, this is a normal person, whose brain is properly functioning. And you see the last image, extreme left hand side image. You see this image clearly showing the central portion, there is no blood flow at all, tracer has not taken, because tracer goes through the blood. So, that indicates the patient is having the Alzheimer disease, because the central portion of the brain is, there is no blood flow. You need not be a doctor to understand this image. And if a doctor sees this kind of the images, so this indicates it's a mild cognitive impairment, that is the Alzheimer has already started. So, patient has already started the forgetting the things, and but may not be complete Alzheimer patient. So, what can be done? At least some preventive medicine can be given. It cannot be cured most probably, but some preventive medicine can be given so that it does not go further, or it can be slowed down at least. So, this is the advantage of the nuclear medicine imaging, which is not possible by the other methods. And the most commonly used radiopharmaceutical for positron emission tomography is FDG, that is called the molecule of the millennium. This full form is 18-fluorodeoxyglucose. So, you can see this is a glucose molecule, all you know, all our cells need glucose for functioning. So, what they have done is that the hydroxyl group in the second position has been replaced by fluorine, and this fluorine is radioactive, 18 fluorine. This is a positron emitter having a half life of only 110 minutes. So, what happens when you inject it in the bloodstream? So, normal glucose, it undergo glycolysis and Krebs cycle through metabolism produce the energy, and here it goes to the cell, but it cannot, metabolism cannot proceed further, because here it is not glucose, but there is something different. So, it enters all the cells, but it cannot go further metabolism, so it gets trapped. Now, the question is, it will go to all the cells, because all the cells need glucose. But do you know what is cancer? Cancer is basically the very first division of the cells. So, when there is a cancer, the mass is much higher. So, what will happen? More tracer will be accumulated there, and you will see a bright spot there, what I was showing them. That is basically the principle of FDG imaging. So, where there are more cells, in cancer there are more cells, because this is a continuous cell division. So, more tracer will be accumulated, because all those cells need glucose, and you will 18F FDG will accumulate more there, and you will see a hot spot there. So, that way we can detect whether the patient is having the cancer. Now, these are the different PET radiopharmaceuticals which are produced in our center and used in our hospitals. So, you can see this is the FDG produced twice, now thrice daily maybe, and there are some other radiopharmaceuticals, like say this is fluoroethyl tyrosine produced weekly, which is used for the brain gliomas. For brain cancer, we use this radiopharmaceutical. And few years back, maybe 2-3 years back, we have started the medical cyclotron facility at Kolkata, that is a 30 MeV cyclotron, and this is at Mumbai at 16.5 MeV cyclotron. So, these are the different radiopharmaceuticals which are produced. Even we have started producing 68 gallium and 201 thallium. This 201 thallium is used for heart imaging in Calcutta Center. Now, with that, I will come to an end of the diagnostic part. So far, what I was telling is to diagnosis only, whether there is any problem in the human body. Now, coming to the treatment, that is how these radiopharmaceuticals can be used for treating the diseases. Am I too fast, or is it okay? Now, you know, this, as I told, radiopharmaceuticals is predominantly used, or therapeutic radiopharmaceutical is predominantly used for the treatment of cancer. So, you know, the cancer, number of incidences in the cancer in India is increasing quite rapidly, and you can see here the statistics in 2022, slightly old, roughly 15 lakh cancer patients, new incidences in India, and the mortality is around 8 lakhs. And it is projected in 25 this year, it will go almost 1.5, almost 1 lakh enhancement, 15.6 lakh, and this is increasing very fast. Every year we are adding maybe 1 lakh new patients apart from the old patients, and these are the major sites for cancer. For male, lung, mouth, prostate, tongue and stomach, and for female, breast, cervix, ovary, uterus and lung. So, if you look in the world scenario, so you can see here, this is the world scenario, and as we come from this side to this side, that indicates the number of cancer incidence per million people. So, it is increase, this side is high, this side is low. So, if we look here in India, okay, we are somewhere here. So, the number of incidences per million people is comparatively less compared to the western world. But our problem is our population. We have 140, even more than maybe 140 crore of population. So, even the incidence is less, the number of cancer patients is high, and our mortality rate is also high. So, how to treat these patients? So, there are many ways you can treat these patients, many techniques are available like hormone therapy, surgery, bone marrow transplantation, chemotherapy, different way of targeted therapy, radiation therapy, immunotherapy, etc. And it is a very tough disease to control. You need to use multiple techniques depending upon the condition of the patients. So, I will concentrate here how the radiation can help in treating the cancer patients, and it can be done by 3 ways. They are called teletherapy, brachytherapy and radionuclide therapy. So, I will try to explain briefly what are these things. So, teletherapy is basically external beam radiotherapy. When you take a powerful say gamma ray or maybe high energy X-ray from a medical accelerator, or particle therapy like proton therapy, what has recently been started in our ATREX center in Mumbai and also available in Apollo Chennai. I think there are only 2 centers who do this proton therapy at this moment. So, radiation comes out from here and patient is lying here. So, this targeted beam, with the targeted beam the patient's tumor is irradiated. So, this is called teletherapy and most commonly used radioisotope is 60 cobalt, because it has a very hard gamma. It emits 2 gammas totaling an energy of around 2.5 MeV. Apart from this, of course, the electron beam can also be utilized. So, these are the machines developed at the Department of Atomic Energy known as Bhavatron. So, this is here is the source, 60 cobalt source is loaded here, and patient as you can see is lying here. The radiation can be tuned, and wherever is the tumor, that portion can be irradiated. It is advanced version has also been developed in, that is called Bhavatron 2, and we have more than 60 or maybe around 70 Bhavatron at this moment in India. I am not sure about the number, and even we have donated this machine to some of our neighboring friendly countries like Vietnam, Mongolia, Kenya, etc. As you can see here, Honorable Prime Minister of India is donating one of the machine. It is a miniature of the machine to, I think, to to his Mongolian counterpart. So, here basically it is a source of very powerful gamma radiation. Now, coming to the brachytherapy, that is another mode. What I told is the teletherapy. Brachytherapy means it is a tiny sealed sources what is kept very close contact to the tumor. As you can see, these are very tiny source. You can see how much small they are, and the radioactivity is inside. So, it will not contaminate your hand if you put it in your hand. And so, these are the sources put in a holder, and like that it is placed in the eye, because it is used for the treatment of eye cancer. We regularly supply 125 iodine sheets for the treatment of eye cancer patients. So, these are called applicators. Here the seeds or this type of the brachytherapy sources are loaded and put it for the treatment of the breast cancer. So, where there is a cancer, it is placed very close to that, and here it is, you can see the patient is being, breast cancer patient is being treated. Here it is the treatment of the prostate cancer, and for prostate cancer usually we do not remove the things, it is permanently implanted in the patient, but for eye cancer it is again taken out after it gives a certain amount of dose as decided by the radiation oncologists that this patient need this much dose. Once the dose is delivered, these seeds retrieved, but for prostate cancer usually you do not retrieve it, it is kept permanently kept in the with the patients. So, you can see here the same thing that we regularly supply for the treatment of the ocular cancer. It is placed in the eye, after a certain amount of time it is taken out from the eye, and you can see this is another one. Very few years back our colleagues have developed 106 ruthenium based agent, and this is basically a radioactive waste. So, it goes into spent fuel, that is after the reactor runs, the fuel what is left out. So, from where we separate this 106 ruthenium, and you can see this is the photograph of eye cancer patient. So, this plaque has been placed, and you see after certain period of time that cancer has gone. This is done in AIMS, All India Institute of Medical Sciences. So, and its cost is almost 1/10 of the compared to the imported devices. So, you can see here the brachytherapy of the prostate cancer, and these are the therapeutic. Now, coming to the radionuclide therapy, where you use the radiopharmaceutical, that is injectable radiopharmaceutical. These are the different radiopharmaceuticals supplied by BRIT, Board of Radiation and Isotope Technology, for the treatment of different kind of the diseases. You can have this information from the BRIT website. I have also taken from the BRIT website. So, I will just explain some of them. So, the most important thing what is used is 131 iodine. It is used mainly for the thyroid disorders. These radioisotopes, which is regularly produced by Shahir, who is sitting with you, he produces it at least 40 to 45 times in a year, almost weekly basis, and we have a huge demand for this. And this is basically used for the thyroid disorder, I told, because these are the two things I told, T3 and T4. You see in T3 there are 3 iodines, and in T4 there are 4 iodines. So, automatically when you inject, we do not inject, basically we ask the patient to drink in most of the times. So, it goes to the thyroid, automatically gets accumulated in the thyroid, or it can be given in the capsule form, like that small capsule, normal capsule. We put the radioactive iodine inside and give it to the patient. They just pop like any other capsule, and it automatically gets accumulated in the thyroid. So, they destroy the overactive thyroid tissues, which is known as hyperthyroidism. This is not cancer, this is hyperthyroidism, where the thyroid gland is much more active than required. Then to shrink the thyroid glands, you know the disease goiter, when it becomes very big, thyroid becomes very big. So, reduce the goiter, this is used, and of course, for the treatment of the thyroid cancer, the cancerous cells of the thyroid. And as I mentioned, that majority of the patients are female in case of the thyroid cancer. Now, coming to the another very important application called peptide receptor therapy or peptide receptor radionuclide therapy, PRT or PRRT. So, I will try to explain what is this. So, when we have cancer in the body, these cancerous cells overexpress some receptors. So, what is receptor? It is basically a kind of protein. So, it overexpresses those receptors. So, if we can target those receptors, we can achieve the target specificity. Now, basically we are injecting the preparation in the patient's body, and there should be some difference between the cancer cell and the normal cell, which we should be able to exploit to get the target specificity. So, these cancerous cells, like as I told, they produce, they consume lot of glucose, they have acidic in nature. So, these are the difference from the normal cell and the cancerous cells. So, these difference we exploit in radiopharmaceutical to get the target specificity. So, here what happens is that when there is a malfunction in the body, when there is cancer, those cells express, rather a little overexpress certain kind of receptors. Normal cells also express some receptors, but these, the concentration of those receptors become very high in the cancerous cells. So, there are some peptides. You know what is peptide? This is a combination of amino acids which are specifically goes or targets those receptors. So, what we do is that we radio label those peptides with the radioisotopes. So, what will happen? This peptide has an inherent tendency to go towards the receptors. So, by that process it will carry the radioisotope to the target cell. So, here I have shown a cartoon. As you can see, this is the cell, the receptors are overexpressed, number of receptors are very high. So, your preparation is coming here and it goes here and internalizes within the cell. By that process you put the radioisotope within the cell and then the radiation comes out and kills the cell. So, this is the concept of peptide receptor radionuclide therapy, and two peptides which are very regularly used all over the world as well as India. One is for the known as dotatate. It is an octapeptide, that is combination of 8 amino acid which is coupled with a bifunctional chelator called DOTA. Why the bifunctional chelator is required? Because I have to attach the radionuclide with it, and we have to attach very stably, because we should not do something somehow attach it and put it in the body. Then what will happen? Once you inject, it will be separated. So, we need a very stable preparation, very stable in vivo preparation which will be stable inside the body. So, these are called bifunctional chelators. So, radioisotope will come here, form a very stable complex with this moiety, and it is connected with this peptide. So, this total preparation will take this radioisotope to the cell. So, this is used for the treatment of the neuroendocrine cancers, and this is the latest development. Somewhere in 2014 it has come, called PSMA 617. Only 3 amino acids are there, that is prostate specific membrane antigen. So, it goes to the prostate and takes the radioisotope to the prostate. So, I will show you some of the examples. So, this is a patient treated with dotatate. So, initially you see this patient has a neuroendocrine cancer. You can see this is a liver basically, you can see lot of extra dots here, hot spots. So, that indicates the cancer burden in the patient. So, first cycle you see it has already reduced, and after 3 cycles you see you cannot see these dots. That shows that the cancer is basically getting controlled by this. So, this is a very commonly used radiopharmaceutical, therapeutic radiopharmaceuticals, and this number may be now maybe around 8,000. So, more than 8,000 patients may be treated in our own hospital, that is called Radiation Medicine Center, a hospital of Bhabha Atomic Research Center, and all over India it is regularly used, and every week now almost 100 patient doses even supplied from BRC only, BRIT. And apart from this, many hospitals they prepare it locally taking lutetium. Lutetium is the radioisotope from us or maybe from abroad, and they prepare at their hospital radiopharmacy and treat the patients. Similarly, this is for the prostate cancer patient. You can see it is not very clear, but you see here these are the additional hot spots. That is the cancer has spread. This is a prostate cancer patient, and he has undergone 4 therapies. This is pre-therapy image, and these are the therapy images after 4 cycles, first cycle, second cycle, third cycle and fourth cycle, and every cycle roughly 200 millicurie of lutetium PSMA has been injected, and you can see these additional, these hot spots are not visible here. So, the disease has been controlled, the patient has almost cured. But please note that it is not always the case. For not all patients it will be like that, it is some of the cases. It is not that it is a 100% success. So, some patients will not respond. It is some example where the patients have responded, and this regularly is used not only in our own hospital. All big nuclear medicine centers in India, they have now regularly using this lutetium dotatate and lutetium PSMA for the treatment of neuroendocrine cancer and prostate cancer respectively. Now, this is another example. This is I have taken from literature, Journal of Nuclear Medicine, which is considered to be the best journal, one of the best journals in nuclear medicine. You see this patient, image is February 2016. You see this extra hot spots, extra dots, I think is very clearly visible, and you see the PSA level. PSA is prostate specific antigen. Normally it is somewhere in the 0 in normal people, normal male, and you see his PSA level is 356.2 nanogram per ml. This is basically a marker. When it increases, See, if it goes beyond 10 or something, doctors will be very worried. It may go due to infection also, but if it is such so high, it indicates basically it has a prostate cancer, very advanced case of prostate cancer. The patient was treated with PSMA, and see, after I think 8 months, in October 2016, you cannot see these extra dots. That means the disease has been completely cured and controlled. And now again, after 9 months, patient have been imaged just to see whether it is relapsing, whether it is again coming back. But no, you see how clear the image is. That indicates this therapy is basically working. But again, I am telling, it is not, you should not think it is 100% that any prostate cancer patient at the last stage coming and this injection is given and he will be cured. It is not the case, but definitely in certain cases it is very, very successful. Now, coming to the treatment of liver cancer, you know, liver cancer is another very prevalent cancer in India, particularly in the state of Tamil Nadu, Kerala. In the southern part it is more, I do not know the reason. So, at this moment, if it is, there are radiopharmaceutical, there are two, one is called SAR sphere, that is basically 90 yttrium level resin microsphere, very, very small spheres where the 90 yttrium has been loaded and it is injected to the patients, or another called theraspheres, that is basically glass microsphere made of glass, and within that the 90 yttrium, that is a radioisotope with high beta energy, has been incorporated. So, what it is done is that it has been injected through catheter basically, because this is a hepatic artery which feeds the liver cancer cells. So, it goes to the liver cancer directly, and this is called, this procedure is called TR, transarterial radioembolization. That means what it does is that it completely blocks the blood flow of the cancer cells. So, once you stop the blood flow, what will happen? It will not go get glucose, it will not get oxygen, slowly it will die, and at the same time these spheres have been made radioactive. So, not only it will block the blood flow, it will also emit the radiation to kill the cancer cell. But the issue is its cost. So, one dose is cost around 10 to 12 lakh rupees if you import. So, it is a very big issue in India, because this is almost unaffordable to a major population of India. So, what we have done is that we have developed our own theraspheres and we call it Bhavasphere. It is again the glass microsphere prepared by the collaborative effort in BRC with the Glass and Advanced Material Division. They have the expertise in making this kind of the microspheres. These are very small sphere made of glass, and what we have done is that we have put 89 inside that. Now, this microsphere they make and give it to us, we put it in the reactor. So, what happens? It undergoes N gamma reaction. So, whatever 89 yttrium is there, it becomes 90 yttrium, and we process it, make it suitable for human application and send it for the treatment of the cancer patients. So, you can see here the first patient we have treated in Tata Memorial Hospital 2021, and this year also we have sent 2 doses to Tata Memorial Hospital just some 15 days back. And our price, though at this moment we are not selling it, we are just giving who wants to use it. Even if we sell, I guess the price will not be more than 1 lakh rupees. We have not priced it. So, the price which was almost unaffordable from 12 lakh rupees or something will come down to roughly 1 lakh rupees. But of course, it is extremely difficult to make those, need lot of expertise to make those glass spheres and make it, irradiate it, process it and send it for the patients. But our Department of Atomic Energy always at the forefront to bring this type of the preparations for the benefit of the patients of our country, and this is one of the very recent developments at BRC. Now, coming to palliative care. So, what is palliative care? Say the cancer has spread throughout the body and it cannot be controlled, the patient is going to die in next 6 months or 8 months, but the patient get lot of pain even it is so high that they are not able to do their own daily work. So, this palliative care means you are treating the patients not for curing, but for doing something so that the remaining period of the life he or she remains, at least can do their daily work, remain painless. So, that is called palliative care. It is not for cure, and there are a lot of radiopharmaceuticals which have been developed. Now, in majority of the cases in our country, what people do is that once the doctor tells that they do not want to spend further money on the patient, because by that process maybe the family has spent lot of money, they do not have resources, and they know this person, whatever, maybe very painful, but they have to, they know that this patient will not survive. So, again spending lot of money is difficult. So, they give the narcotics, patient remains painless, but camouflage condition, cannot do anything. The best way to treat this, you inject some radiopharmaceutical, because it will reduce the pain, but at the same time it has no side effect. As I told that radiopharmaceutical has no pharmacological effect. So, there are many radiopharmaceutical, and these two are almost discontinued in all over the world. Earlier we used to supply 32 phosphorus, now we have stopped it. Strontium is very difficult to produce, we do not have, and hardly any people uses in India. And these are the other thing, all available. We have a bunch of radiopharmaceutical, and whatever doctor wants, we will be able to provide. And this ready to use lutetium EDTMP radiopharmaceutical, this is completely developed in India. This we have only developed, and now it is used in multiple countries of the world. So, I will show you, this is the use of our radiopharmaceutical. So, this is the MDP as I have shown earlier. This patient is having some extra dots, you can see these are the hot spots, and he has been treated with the lutetium EDTMP. Again, it is not for cure. This patient cannot be cured, it is only for the palliative care. Now, coming to almost in the last part, it is called radioimmunotherapy, with which we are recently working, that is antibody guided tumor targeting. So, I know you know what is antibody. So, when some foreign object enters human body, body due to its own mechanism tries to fight it. So, that foreign thing is called antigen, and what body produces is called antibody. So, these antigens, even when there is cancer, the cancer cells also produces different kinds of antigens. So, if you can develop the corresponding antibody and radio level those antibodies, what will happen? You will have a targeted missile kind of thing, because antigen and antibody reactions are very, very specific. One particular antigen reacts with particular antibody only. So, if we can radio level the antibody and put it in the patient's body, it will automatically go to where the antigen is, and those mainly are the cancer cells that is producing more antigen. So, we try to radio level antibodies. Here I have tried to show it. As you can see, this is the antibody, basically a large Y-shaped molecule, almost molecularity is 1,60,000 Dalton, and here is the radioisotope joined with a bifunctional chelator. So, it takes the whole preparation towards the cancer cell, because that expresses lot of antigens. So, due to this specific antigen antibody reaction, this radioisotope also goes to the tumor cells or cancer cells. So, we are working with different kinds of antibodies, mainly with one antibody called rituximab, that is used for the non-Hodgkin's lymphoma, that is for the treatment of blood cancer, a type of blood cancer, and in India lot of young people die as there is no medicine for this. So, we are trying to develop it. This is trastuzumab, again it is for the breast cancer patients who overexpresses Herceptin receptors, and nimotuzumab, again it is for the breast cancer patient, and you can see these are some of the clinical trial images, that is we are doing the studies in the patients in collaboration with different hospitals, as you can see with Tata Memorial Hospital, Kovai Medical College and Hospital. So, these are basically approved to some extent in India, but not regularly supplied at this moment, very limited supply we do with the physicians who are interested in treating the patients. Now, coming to the last application, that is a non-cancerous application of therapeutic radiopharmaceuticals. So far what I told is treatment of cancer, and yes, majority of the cases therapeutic radiopharmaceutical is used for the treatment of cancer. But there is one application, at least I can tell you, already I have told one, that is for the goiter, hyperthyroidism, these are non-cancerous applications. This is another one called radiation cyanovectomy. So, what is radiation cyanovectomy? That means your treatment of the arthritis using the radioactive material. So, this arthritis can be treated in different ways, like you can do chemical cyanovectomy, that is where you inject some poisonous chemical to kill the excessive proliferation of the joints which causes the pain. Surgical cyanovectomy, where you do the surgery, and other way is radiation cyanovectomy. And the advantage of this is that there is a significant pain relief and improved joint mobility, but no long time hospitalization is required. It is an almost day care process. Morning the patient can come, it is preparation is injected, and after some time the patient can go to his or her home, and it is a cost effective compared to other modalities. So, you see there are different isotopes which we have radio labeled with one preparation called hydroxyapatite. HA, hydroxyapatite is basically our bone matrix without the organic part. Our bone is basically hydroxyapatite particle with some organic material inside that. So, what we have done, we have removed the organic material, we have synthesized the inorganic part. It is basically a type of isopolyacid of calcium. We have synthesized it, made it a particle size of 2 to 10 micron, and some radioisotope has been loaded on those particles. So, they are different isotope. Why different isotope? Because we need to load the isotope depending upon the size of the joint. So, if it is a big joint, like I want to treat a hip joint, I need an isotope with higher energy, like say 90 tritium or 188 rhenium, those are high energy beta emitter. If I want to treat the medium sized joints, like say like elbow joints, I do not require such a high energy beta. What will happen otherwise? It will irradiate the surrounding cells also. So, I need a medium energy beta, like say 175 ytterbium or 177 lutetium, this kind of the isotopes we can load in HA. And if I want to treat the small joints, like say phalangeal joints, like this, digital joints, like this, even I do not need mid energy also, I need low energy beta, for which we use 169 RBM. So, we have already developed two, 177 lutetium HA and 90 tritium HA. These are regularly supplied, and we have the approval from the regulatory authorities, and per dose is given roughly at 8,000 rupees. If we want to import, it is definitely more than 50,000 rupees. So, we supply it around 8,000 rupees, and we monthly once it is supplied from Board of Radiation and Isotope Technologies. And for the small joints, we are yet to get, we are working on it, but we need the regulatory clearance before we can give it to the patients, that is 169 RBM HA. So, these are the two things what I was telling, these are we are regularly supplying to the patients from Board of Radiation and Isotope Technology. So, I will just show complete my presentation by showing you a list that what Department of Atomic Energy is doing for the healthcare applications using the radioisotopes. In the last 5-6 years, we have developed 23 products, out of which 14 are therapeutic based different radioisotopes I have noted listed, and 9 diagnostic products, and these are supplied either as per the demand or something which have a very high demand regularly, and here you can see the cost difference. So, Dotatate, that is used for the neuroendocrine cancer therapy, now we supply from this year 15 days monthly twice. Our cost is here, and you can see the cost, import cost. This is only the cost of medicine. Apart from this, hospital charge and other thing will be added. So, this is the PSMA that about which I am telling. This is the prostate cancer patient treatment. This is the cost with which DIE is supplying, and this is the import price. And these are some radiopharmaceuticals which are not yet priced. I told that these are we are doing, giving it at this moment without any charges to the interested physicians. You can see the list is quite long. These are the things what I am telling, that radiation cyanovectomy, its cost is 8,000 rupees per 10 millicurie dose, and you can see the list is quite lengthy. So, apart from this, we not only Department of Atomic Energy not only do the research and supply the radioisotope based product for healthcare application, we are also in the manpower development, because as I show when I started this presentation, that our share of radioisotope for in India is bare minuscule, just 1.5 to 2% of the world's uses, and we need to increase it. So we need not only the infrastructure, not only the reactor, not only the cyclotron, we need manpower also. And DAE is contributing in developing the manpower. We have several programs, as you can see here. For the doctors, we have DRM, DNV, MD in nuclear medicine program run by the Department of Atomic Energy. For the nuclear medicine technologists, particularly important here, those who want to join from the physics, Bachelor of Physics, Master of Physics and Chemistry background, we have several programs like BSc Nuclear Medicine, MSc Nuclear Medicine, Diploma in Medical Radioisotope, Diploma in Medical Radioisotope Technologies, several programs for the radiopharmacist like again BSc Nuclear Medicine, MSc Nuclear Medicine, DMRIT, for radiologist, Diagnostic CT in PET CT. So these are the different courses. For RSO, you need an RSO also, Radiation Safety Officer, if you want to use in your facility some radioactive preparation. So these are the different type of the courses which are done offered by the Department of Atomic Energy, either at BRC or in Tata Memorial Hospitals. And you can see here the 70% of the nuclear medicine physician and technologists who are heading the various premier institute of our country, like All Indian Institute of Medical Sciences in Delhi and multiple places, PGIMER, Postgraduate Institute of Medical Education and Research, that is in Chandigarh, JIPMAR, that is in Puducherry, CMC Vellore, they are all trained basically at BARC. So it is not only that we do research, development and supply, we also train the manpower for the future generation, for the future needs. And with that, I will come to the conclusion of my presentation. So thanks to the exemplary vision of Dr. Homi Jahangir Bhabha, we made a very early entry in the field in the production of radioisotopes. Basically, we started somewhere in the 1960s. 1956, the first reactor came, that is the Apsara reactor. That is the first reactor in the Asia. And within 3-4 years, we have started producing the radioisotopes, albeit in very small quantity. And thanks to the multidisciplinary teams of DI units and strong support of the department both in R&D and production services, availability of the most of the radiopharmaceuticals has been ensured for the nuclear medicine practices in India. So we don't have the problem of the availability, only issue remains is the quantity, because our population is very large. To cater the need of all the hospitals is difficult, but we have the technologies for all the radiopharmaceutical, almost all the radiopharmaceutical known all over the world. So we need to only enhance our infrastructure. We need more cyclotrons, more reactors, and nearly 500 million procedures are performed every year for the benefit of the patients in India. And there are in India 300 nuclear medicine centers, 85% are in the private sector, 250 plus PET gamma cameras, 24 medical cyclotrons, 280 PET CT units and 3 PET MR units in India. So it is growing very, very fast. This data may not be correct even, it may have increased further, because I heard it is now closing to 500 actually. So every year we are increasing lot of nuclear medicine centers, and now it is not only available in metropolitans, even tier 2, tier 3 cities are also having the nuclear medicine centers. And almost all the nuclear medicine centers depend on BRC bridge for most of the reactor based radioisotope and radiopharmaceutical products. So I think you are now convinced that radioisotopes is a vital component of modern healthcare. So with that, I conclude my presentation and thank you for your kind attention. So I think I am in time. So we have 5-10 minutes
Yes,
of
yes.
time for discussion. So I'll be happy if there is any question.
Any queries? Yeah.
Sir, thank you very much for wonderful lecture on this topic. So I have one question about the Bhabha spheres. So can you explain which type of the material actually you used to prepare such a Bhabha spheres?
Okay, sir. Sir, basically it is glass. It is a glass microsphere.
Okay.
It is basically
These are the porous materials?
this has been
Porous,
yes.
like aerogels? Silica aerogels?
No, it is basically we don't means I think you are asking whether you can put something there. It is not like it is a fixed preparation.
Okay.
We have put some yttrium there, 89 yttrium, cold yttrium there, and the full glass we sent, the small microsphere we send it to reactor to make it 90 to 89 will be converted to 90 yttrium, and then we bring it, process it.
So
and
basically it is a glass.
it is basically a glass.
Okay.
It is a non-biodegradable, but we are presently working with IIT Kharagpur to develop some biodegradable glass microsphere also.
Okay.
So why to put something in the patient which is not
Okay.
biodegradable? So we are trying that, but again the issue is that that material should be radiation stable also, because we are putting it in the reactor.
So can we think to use the aerogels because they are also porous small spheres?
See, sir, we have to see first whether such a thing is stable under the very intense radiation, because we have to put it in the reactor. So what is the radiation stability? It should not break down after reaction. That's the reason the glass is preferred, because it is very, very stable preparation.
Okay, so
So we have to see, so we need a particular size. It's not that any size of glass you can use. It is a very specific
so what
size.
is the approximate size we require?
It is basically somewhere between 20 to 60 micron.
Okay.
Micron. It may be average, maybe 38, 40 micron, and range is 20 to 60.
Okay.
So the size should not alter after we do the irradiation. It should not break down. So if that material is stable, it
As
can
per
be
my best knowledge, actually aerosols are stable at the high radiation dose.
then
Yes.
we can see,
Yes.
can we make a microsphere with that?
Yes.
So
yes.
we
So
can
whatever
of course
actually you have shown that picture, no, similar kind of the nature actually they have. They are most stable. So we will discuss, sir.
Yeah,
afterward.
sure. I'll be happy to discuss. it.
Yes, thank you, sir.
Good morning, sir. Is there any chance for a reduction of carcinogens present in sewerage or in water pollution or by irradiation process? Is there any chance to reduce the carcinogens present on food or due to the pesticides? Now the rate of cancer is getting increased in an alarming rate. Is there any chance to decrease the carcinogens by food irradiation or sewerage sludge?
Madam, we do sludge hygienization. Basically, it reduces the pathogens that causes a lot of diseases. We have certain plants run by Department of Atomic Energy in 1 or 2 places. But it is not proven that whether we will be able to reduce the cancer, because we don't, actually people don't know what is the cause of cancer. It's a multiple causes. See, one of the reason is told that smoking causes the lung cancer. Yeah, it's correct. But I can tell you or show you multiple people who smoked throughout their life has not got cancer. So it is not absolute. It can only tell if this increases the cancer. So it's very difficult that way. But definitely sludge hygienization is a process which is taken up by the DAE, and we have a running plant at Baroda also. And I think one is coming in Indore also. So where the sludge hygienization will be done by using the radiation, but not to reduce the cancer, but to reduce the pathogens and use those sludge as manure.
Thank you. Thank you, sir.
Any further questions?
Yes, I expect some questions from the students.
You can also ask during the lunch if you are a little afraid of asking now.
No need to be afraid, even you can ask in Telugu also. My colleagues will translate it. No problem.
Then I can translate.
Yeah, please. If you have any doubt, don't feel shy. Please ask. Yes, please.
Yeah. తెలుగులో అడగొచ్చు మీరు.
Sir, can we convert the therapeutic elements into diagnostic elements?
No. No.
Then why, sir?
Because their properties are different. So therapeutic radioisotopes basically emit beta and alpha. And for diagnosis, we need the gamma radiation. So pure gamma emitter. We don't want beta or alpha. They are completely different class. So I think the answer will be clear tomorrow when we will teach the production, when we will tell about the production, you will understand what is their differences, why they cannot be converted to each other.
Thank you, sir.
Yes, please.
So, for the drug delivery, actually we use the biomolecules or some biological cells. So, whether they get damaged because of the nuclear medicine, these particular carriers, I am asking about the carriers.
Yes, I got your questions. Yes. No, because we see their stability first. It's not that anything and everything we can radio level and put it in the patient. So, we first need to check their stability, and the stability is not only checked in the laboratory. We have to check in phosphate buffer saline first, then in human blood serum also we check, because many times your preparation is stable in the laboratory, but once you put in the blood serum rather I will tell, it is not stable, because blood is a very complex matrix. There is a lot of competitions to snatch your metal, that is radio metal, or maybe your ligand what you are using, the carrier moiety, that tries to complex with other metals which are present in the blood. Our blood has lot of other things, zinc, magnesium, calcium, so many things. So, it has to be stable there. So, we check all those stabilities before we even go for the animal studies. So, if it is getting damaged due to radiation, we will not use it. Even what we do is that once we put it in the animal, say a small animal like rats or mice, we take out their blood after certain time, say maybe 3 hours or 24 hours, and we bring it back and check in the HPLC whether the stability still remains. If it is not stable, if it is forming something else, then it may not be useful, maybe. Sometimes it changes due to metabolism, that is different, but original structure should not be changed.
Thank you, sir. So, I thank Tapan Das Garu for his very interesting and wonderful lecture. So, today he gave a clear idea of diagnostics using radioisotopes and also in therapeutic applications. So, he discussed about the advantages of the diagnosis using radioisotopes over the other techniques like X-ray or MRI, and also he discussed about SPECT and also positron emission tomography, and I think most of the students are actually hearing the word tomography today for the first time. So, he clearly explained, and then he also explained about teletherapy and other therapeutic applications using radioisotopes, using cobalt-60 and iodine-131, and also PRT techniques, and how to treat different cancers using radioisotopes. Sir, thank you for a very wonderful and very clear lecture, and I strongly believe that these insights you are given will be very useful for our students, and today we learned many things from you, sir. Thank you very much. We have a QA session now. Please be seated. We will have a QA session as usual. After that, we will go for lunch.
Good afternoon all. So students, you are ready for quiz? So yesterday I have seen most of the students write some notes from slides. It's very good. So today I prepared some tricky questions. So during the practical, we'll give one feedback form to you, You have to fill that form and return to us. So those students who are hesitating to fill the form, will provide an email ID. So please mail to us. Okay? So ready for quiz? So the first question is, yesterday was very healthy competition between Rajahmundry Government College and Andhra University of course from Nannaya University also. So today, see what happened. Okay, the first question is, George Hevesy discovered an element. George Hevesy discovered an element. What is that element? Oh, so many hands. Nice. So the t-shirt guy.
Radioisotope tracer. Element, what is that element?
What is that element? George Hevesy discovered one element. No, no, don't see the notes. No, 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 no.
No, he'll select. Let's
Sir, last. That, this one, this row. This. Yeah, yeah.
Fanate animal, sir.
What?
Fanate animal, sir.
No. Sir, last.
Element number 72, half name.
Yes, hafnium 72. Come forward, tell your name, university.
Sir, my name is Suresh. I am studying BSc second year, UG. Arts College. Government Arts College.
Today students are highly energetic. So the next question is, in radio analytical technique, what we induced for experiments? In radio analytical technique, what we induced for experiment? Yes, you. Neutrons? No. Sorry?
Isotopes and neutrons.
Yes, exactly. Radioactive isotopes we induce. Come forward. Come forward.
My name is Vandana. I'm a Nuclear Physics, Department of Nuclear Physics, Andhra University, Visakhapatnam.
The next question is, how we can measure the volume of blood? What is the technique's name? Oh, so many hands again. Choose.
Isotope dilution, sir.
Speak loudly.
Isotope dilution, sir.
Right, excellent answer. Come forward, introduce yourself.
Hello. My name is Gopal Krishna. I am studying second MSc Physics in Government Autonomous College, Rajamahendravaram.
Congratulations. The next question is very simple. What is the abbreviation of NAA? So many hands, so many hands.
Neutron analysis, neutron activation analysis.
Right, good answer, excellent. Come forward. Peru Cheppamma, Peru College.
My name is Vijaya. I am studying BSc Physics second year, Government Arts College, Rajahmundry.
కంగ్రాచులేషన్స్. మీరు భయపడొద్దు, కరెక్ట్ ఆన్సర్ ఇచ్చారు, గిఫ్ట్ వస్తుంది. సో పేరు చెప్పడానికి భయపడుతున్నారు. ఓకే, నౌ వాట్ ఈస్ ప్రాంప్ట్ గామా రేస్? ప్రాంప్ట్ గామా, వాట్ ఈస్ ప్రాంప్ట్ గామా? ఓన్లీ సింగిల్ హ్యాండ్.
Prompt gamma is like a neutrino activation analysis. It is used to detect like for SPECT and the for PET imaging, like to detect the radionuclide organ part in the tissue itself. No?
Now what is meant by prompt gamma?
Prompt gamma. So production of gamma rays from the source itself to cure the antigens in the body, no, which are malfunctioning.
No. Anybody? Prompt gamma. Faculty? Faculty, anybody? ప్రైజ్ నాకు వచ్చేస్తుంది.
Which is used to detect the landmines.
No, no. Not application. It's what is prompt gamma. That student backside. Yeah. Huh? Compound nucleus దగ్గరకు వచ్చావు చాలా. That student.
When a compound nucleus emit an neutron or anything, then when it incident with electron, it will give prompt.
చాలా దగ్గరకు వచ్చావమ్మా. It is very close.
That's it.
కరెక్ట్ ఆన్సర్, గ్రేట్. సో ఆన్సర్ వచ్చేసి మనకి ఒక ఎలిమెంట్కి న్యూట్రాన్ ఇచ్చినప్పుడు దట్ విల్ కన్వర్ట్ ఇంటూ కంపౌండ్ న్యూక్లియస్, రైట్? దట్ ఈస్ ఇన్ ఎక్సైటెడ్ స్టేట్. సో దట్ విల్ emit gamma rays. So that is called prompt gamma. Next question is, radioisotopes are used in healthcare. In what ways? Radioisotopes are used in healthcare. In what ways?
Diagnostic and therapeutics.
Yes, good answer. Diagnostic. Come forward, tell your name.
I'm Sheikh Shahida from 2nd MSc Physics, studying in Government College, Autonomous Rajahmundry.
Congratulations. Now the basic question again. What is meant by radiopharmaceutical? What is the meaning of radiopharmaceutical?
When the pharmaceuticals industries use radioisotope as a drug or as a medicine in the medicine department itself, na, so it becomes radiopharmaceuticals.
Yes, correct answer. Come forward.
Myself Simrat Kaur and I am studying in Delhi University.
She came from Delhi, sir. The next question is, which radioisotope is used worldwide more than 80% for diagnostic purpose? Oh, so many hands.
Technetium 99M.
Yes, exact. Please come forward.
My name is C.H. Triveni, Government College Autonomous, 1st MSc Physics.
Congratulations. So the next question is, why we need radioisotope to inject in human being, though we have X-ray, MRI, CT scan? Again, I repeat, why we need radioisotope to inject in human body, though we have X-ray, MRI, CT scan? What is the advantage of this nuclear medicine? నీకు వచ్చిందా ఆల్రెడీ? ఓకే.
X-ray is an anatomic
తెలుగులో చెప్పు, ప్రాబ్లం లేదు.
దాంట్లో ఓన్లీ అనోమెటిక్ ఇన్ఫర్మేషన్ వస్తుంది సార్. ఇందులో అయితే మనకి అనోమెటిక్ అండ్ అలాగే ఫంక్షనల్ ఇన్ఫర్మేషన్ కూడా వస్తుంది.
Yes, great answer. Exactly. Come forward, come forward. Perfect answer.
I'm Stella from Autonomous College Rajahmundry, MSc first year physics.
Andhra University, what happened? ఈ రోజు maximum prizes Rajahmundry Government College కి వస్తున్నాయి. Come on, next question is, which radioisotope is used for thyroid scanning and therapy? Thyroid scanning and therapy ki which radioisotope use చేస్తారు? Yes.
31, sir.
Sorry?
Iodine 131.
Yes, correct answer. Please come forward.
So I am Mohan. I am from Andhra University, Department of Nuclear Physics.
Andhra University. Next one is diagnostic radioisotope having which type of radiation? Diagnostic radioisotopes having which type of radiation? Even first like ఆమె చెప్పింది ఆల్రెడీ.
Gamma radiation.
Gamma and one more.
I know only gamma.
There are two. There are two.
Positron.
Yes, positron. Yes, gamma and positron.
I'm Sri Gautam from Government College, Autonomous.
The next question is, what is the abbreviation of SPECT, S-P-E-C-T? Last girl, white color dress. Yeah. SPECT, S-P-E-C-T.
Single photon emission computed tomography. Single photon emission computed tomography.
Very good. You are writing important points from our slides. Very nice. Yes, they are writing. Yes.
Myself Dharani, I am from Andhra University. I am studying MSc Nuclear Physics Department, second year.
Next, it's a you have to explain what is cancer. What is cancer, right?
Cancer is a disease in which cells are divisible uncontrollably and destroy the tissues of the body.
Yes, excellent answer. Very nice.
I am Pradeep from IASC Bangalore.
Nice, very nice.
Thank you.
Okay, next question is, what is teletherapy? What is teletherapy? This white color. Yeah.
It's an external beam radiation therapy.
Excellent answer, very good. Therapy is given from external, not from inside body, okay? Good answer.
I am Kavya from Adikavananaya University, Rajamahendravaram, Department of Physics.
Yes. The last question for today's session. Why palliative radiopharmaceutical given to cancer patients? Why palliative radiopharmaceutical given to cancer patients? Last chapter, sir.
This is from the last slide actually.
Why? ఎందుకు ఇస్తారు palliative agents? Sir, అమ్మాయి సార్ అమ్మాయి ఎస్ సార్ మీ పక్కన
Because it is a pain relief.
Okay. Palliative agents are given to pain relief because cancer overall body లో స్ప్రెడ్ అయితే పెయిన్ చాలా ఎక్కువ అయిపోతుంది, దాన్ని రిలీఫ్ చేయడానికి palliative agents ఇస్తారు. ఓకే, గ్రేట్ ఆన్సర్స్. ప్లీజ్ కమ్ ఫార్వర్డ్.
Myself Banu, I am studying MSc first year in Department of Physics, Government College Autonomous, Rajahmundry.
Congratulations to all who won the prizes. మిగతా వాళ్ళు రేపు ప్రెజెంట్, రేపు లాస్ట్ సెషన్ ఉంటుంది. థ్యాంక్ యూ.
So now let us go for lunch. After lunch, you immediately come to the lab for the hands-on experiment session. Exactly 2 o'clock. Okay.